So the primary purpose of this video series is going to be for analyzing not just algorithms, but also primarily pieces that are going to be utilized not just in computer science, but also for interviews. And we're going to be starting off with something called the Big O. So really quickly, and we're going to be doing this all in the Jupyter Notebook. Primarily because it's not that difficult enough that we have to use PyCharm, and it's also a little bit cleaner looking. So why analyze algorithms in the first place? So an algorithm, don't get nervous about the word, it's just a procedure or formula for solving a problem. Some of them are so useful that we've given them names like merge sort or bubble sort, etc. And then one of the important things we're going to come across, you're going to see very quickly, is how can we compare the algorithms to know which is better? And by better, it's going to be a relative term to the task at hand, but typically there's going to be two avenues for analyzing if an algorithm is better than another, and that's going to be either by speed, time of completion, and that's going to go into its scalability, and also memory, its size allotment, and its requirements, and so forth. So really quick, let's jump in. So in this first segment of code, I said, imagine think about this function. This is just defining a function called sum of one. It's taking one argument, n. So then we have final sum equals 0. So we have an object final sum, and we're giving the assignment of 0. And it says for x in range n plus 1. So we just have a for loop here. Range is going to be whatever we define it for in terms of the n. So n plus 1 equals final sum plus x. And then we're returning the final sum. So I'm just going to shift enter so that it actually loads into the Jupyter Notebook. And then I have here sum 1, and I'm calling 5 as the argument. And you'll see that it prints out 15. So what this did was, with the object having the argument of 5, and the formula, essentially the algorithm for this, was for x in range. So for each number in range, n plus 1, n was 5. So in 6, you have to remember for range, we started 0, so we had to add that 1 if we wanted to really get 5 actual numbers. So because 0 is not going to have any implication for addition. And the final sum was starting at 0. So if we did 5 times 4, we're going to have 9. 9 plus 3 is 12. 12 plus 2 is 14. 14 plus 1 is 15. So of course we got the answer to be 15, so that's appropriate. So let's see what this is all going towards anyway. So again, this is a function that we've created defining a sum of 1, and we got a result of 15 when n equals 5. We're going to go down here now for this one, and let's assume that you gave me this function. You called it sum2, also taking only one argument of n. And you, instead of doing a for loop, you're just returning n times n plus 1 divided by 2. And let's see what we get. I'm going to shift enter through that as well. And same argument of 5. And we also get 15. Same exact function. If you actually did this math by hand, of course, PEMDAS is going to hold place, so parentheses are always going to be first. So you would have had 5 plus 1, which is going to be 6. 6 times 5 is 30. 30 divided by 2 is going to be 15. So what's the point of this? Essentially, we got the same answer with two very different functions. That's essentially that's the point of this. So this is my function I created, and this is the one that you created, both getting the same result. So function 1 is, someone's going to complain about that, right? FU. So function of sum 1, it's using a for loop to iteratively add across our range of plus 1. So here's our for loop, and we're just iterating over the range that was dictated by the input n. And it's adding across that range. Number 2 is simply just taking advantage of a formula. It's a formula base to solve a problem. Both of these are technically algorithms, because remember the algorithm is just a procedure or a formula for solving a problem. So we're solving a problem, and here we're solving a problem. This is just more formula based, and this is an iterative for loop that we're running. So now the question is going to come, how do we compare them? How do we determine whose function is better, mine or yours? And that's going to become relative to what it is we're trying to determine defines as better. So we have to objectively be able to compare them. And the two avenues I mentioned before that we can do that for is memory, which is space allocation within the computer, or the time to run. How much time is it going to take to actually run that software? So we're going to use built-in magic commands in the Jupyter Notebook. Sometimes I might call it IPython. That's the old connotation, because back then it was just Python, and now it's multiple languages, so they call it Jupyter Notebook. So first off, this is a magic command using the percent sign, time it, and I'm saying I want you to time it for the sum of one function with an n of 100. So I'm going to shift enter that, and right now what it's doing that for loop. So there we go. We got 100,000 loops, best of 3, 3.74 microseconds per loop. And then I'm going to do the same magic time at sum2 with 100 as the input. And then, oh, it's doing the computation now. It took a second there. Depending on your computer, it's going to determine if it happens faster or slower. So for the same n of 100, which we know that they're going to give me the same answer, and you can ignore this for right now, it's just talking about caching. Best of 344, but now this is nanoseconds. So, and I put down here, just for those who may not know, micro, which is up top here, is 10 to the minus 6. Nano is 10 to the minus 9. So that means nano is a smaller number by a factor of 3. And so this is faster. So in the two different functions we had, function of sum1 and function of sum2, for the same n, my algorithm, your algorithm was a function, was much, much faster. You were on nanoseconds, I was on microseconds for time of completion. But now that's not necessarily the end-all be-all, because that's the time of completion on my computer. Your computer, the time of completion might be faster or slower. Now, of course, granted, we're talking micro and nanoseconds. That difference can get very large, and we have much larger inputs to deal with. And some systems will be faster and slower, but at the end of the day, regardless, for loops are always going to be slower. And that's why we try to avoid them, and especially machine learning, artificial intelligence. So now that we have that, I have your smallest number is obviously faster, we know that. So we can't rely on just time to run, because again, all computers are different. Hardware is going to be different. Some are faster than others. We want this to be hardware independent. And that's one of the big takeaways, because as you know, hardware is constantly changing. So how can we objectively determine if one function is faster or slower, or rather is better or worse than another function, if we can't use the time parameter per se because of the objective nature of different computers? Well, that's where the big O comes in. So the big O is a way that we can objectively compare the efficiency of those two algorithms. So we're going to compare the number of assignments of each algorithm. Now there's some key phrases here that we're going to run through, and this is what I want you to be cognizant of. So we're going to compare the number of assignments that each algorithm makes or has to undergo. So for the original sum1 function, I'm going to read this and I'll go back up to it and show you what I mean. The original sum1 function will create an assignment n plus 1 times. We can see this from the range-based function. This means it will assign the final sum variable n plus 1 times. We can then say for that problem of n size, in this case just a number n, this function will take 1 plus n steps, and this 1 is going to become meaningless. So going back up to function number 1, or sum1, what it's saying here is that the allocation that this is going to require in terms of an assignment, it's only the assignment is this. So if my n is 1, it's going to have two assignments. It's going to have the assignment of 1 and then the assignment of 0, because again we're dealing with indexing of 0 and it's ranging. If my n is 3, then we're going to have 4. It's going to be the assignment's going to still be n plus 1, because whatever the n is going to be, it's going to be linear is the point. That's what we're going to be looking at here. But there's only one assignment that's necessarily going on within this. And our first assignment is 0, and then that assignment is going to keep changing based on an order of n. The n notation allows us to compare the solutions and algorithms relative to the size of the problem. So since sum 110 and sum 1 of 100,000 would take very different times to run by using the same algorithm, we can also note that n grows very large. The plus 1 doesn't have much effect. That's what I was referring before. Some of these constant numbers, essentially, when you start to get to numbers like infinity, or if you're familiar with calculus, when we get to limits, the constant numbers just drop off. They no longer have a real effect on the ultimate coding, and you'll see that in just a minute. So how can we still quantify this? How can we still compare the functions? And that's where big O notation comes in. It's describing how quickly the runtime will grow relative to the input as the input gets arbitrarily large. And again, this is how we're going to measure one algorithm over another, or even one, different coding aspects, like using NumPy in an instance, so it can be a heck of a lot faster than if we were using a built-in list sequence in Python, using data frames instead, also utilizing pandas. So it's all the big O. What I want you to put in your head is how well can it scale as the data increases, because big O has a lot to do with scaling. And that scaling can either be in time or it can be in memory. So we're comparing how quickly the runtime is going to grow, not the exact runtimes, since those are going to depend on the hardware. So at least this way I can know it doesn't matter the system. If I have two different algorithms, I can tell you that one algorithm is going to have some element of time and this other algorithm is going to have a comparatively different relative amount of time. Regardless of the hardware, one's going to be faster than the other. if I can see the code and I do the big O notation. So as the n gets arbitrarily large, we're only worried about the terms that will grow the fastest as n gets large. So essentially, if you're looking at an algorithm, and if you're trying to, which we're going to get down to in just a second, you're trying to determine which element in that code is the driving factor, which one's going to actually impose the limiting behavior on the execution of that code. Well, that's going to be your big O, and everything else is essentially going to drop off. And in math, that's this idea is called asymptotic analysis, which is just describing limiting behavior. So it's kind of looking at a whole picture. So we're going to get to this guy in a second. So asymptotic analysis is looking at this return here and pretty much saying, who's the limiting factor in here? Who's going to limit what my n is going to be able to do? Which one of these guys is going to mess with scaling the most, or have the most impact or the least impact on scaling, and then you can go from there. So again, which part of the algorithm has the greatest effect on the final answer? Which part of the algo is the real bottleneck? Which is the limiting factor? As for the syntax, someone can be said to be, this is the notation here. So this is a big O of n, since its runtime grows linearly with input size. So let's go back up to summa 1. So what we're saying is, again, this was big O. If I was to do it in that notation, it was essentially just this. But again, the big O, that was going to be the objective nature of big O notation for this linear event. But the 1, as n gets larger and larger and larger, this number 1 falls off. So when n is 1 or 5 or 10, you'll see an impact of the 1. But even just getting to 100 and then 1,000, this 1 becomes meaningless. So we end up with a big O notation n. And again, this is not supposed to make a lot of sense to you just yet. It will as we get further down, when you can see the stuff in a graphical analysis. So I wanted to bring this idea again of describing limited behavior from an asymptotic analysis standpoint. So here I just created a function called big O with one argument n. And this is simply just returning 45 times n cubed plus 20 times n squared plus 19. And if I call big O with an n of 1, I'm just going to get 84. And if you wanted to do that math, you absolutely can. Just don't forget you have to do operations. So it's 1 cubed times 45, and then 1 squared times 20, and then plus the 19. And you're adding all it together. So if we just did 1 of the variable, we're going to get 84. So what happens if I do just 2? We automatically jump from 84 to 459. So what I wanted you to see is that just looking at these two here, all we did was change n by a factor of 1, correct? And yet our results substantially changed. But the point is that this 19, it had an effect here, even if from a percentage standpoint, when n is 1, 19 had an effect. But when n is just 2, the 19 is pretty much becoming meaningless. So this would not contribute to our computational intensive time because it's not really having any kind of an overall effect. It's not limiting how we're progressing in terms of scaling. So what happens if we go to a big O of 10? So now we're up to 47,000. So now looking back at our piece here, I'm going to get to the second. Going just from 1 to 2 to 10, the 19 we already know is pretty much out of the picture. 19 is not going to make a big difference here in terms of computational intensive requirements. So then the question is going to come down, which one of these is it? I'll tell you right now, you ignore the constants, never look at constant numbers. So what we're really focusing on is n cubed and n squared. And then we're pretty much saying which one of these is going to be the bottleneck, which one of these is the limiting factor for this particular function. Well, it can be seen that the 19 doesn't hold much weight anymore, and we came to that conclusion already. The 20n squared in this case is 2,000, so out of 47,000, if we took out 2,000, we're not that far off. If you do 45,000, if we get rid of the 19. So again, 45,000 and 47,000 is not that big of a difference. So we can pretty much conclude that the n squared is not going to be the limiting factor within this particular function. So then we have the constant 45 don't care about per se, but the n cubed I do. And with our n of 10, it's going to be 45,000. So 45,000 and 47,000 have much more of a percentage-based impact on its outcome of the performance of the calculation of that particular function. So in this function, this entire piece here, you would say this is essentially going to be your controlling big O. This is what's going to determine your scalability. This is what's going to determine your limiting factor. This is what's going to determine who's going to have the biggest bang for your buck within your function, and which is going to require the most computational time in your system. So this part of the algo that really has a lot to do with the final answer as the data scales. It's not going to be the 45 again. Here we have, it's not going to be the 45, but it's going to be the n cubed. So this algorithm has an order of n cubed. So it's a big O Whoops-a-daisy. Let me put this in here. So this is going to be a big O. And then we'll just keep it this way. That would be the order for this particular function. Now what I have here, this is just a big O complexity chart. We have horrible, bad, fair, good, and excellent. So what this is showing that these are different elements, and then we have the operations. So if your function has a big O of 1 or a big O log of n, which is still going to be quite linear, you can see that our performance here, as n grows, n's getting bigger, 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 and this is the operations, the amount of operations that be performed. You can see that we're in the excellent range here, excellent and good range for those particular big O's. But then once we start to get to, this is O with the function of n, which is very much like our original function that we did, sum of 1, you can see we're in a fair from a performance standpoint. As n grows, so too does the time, but the complexity of the nature that is not obscene. And then we start to get bad once we get to big O n log n, and then we're getting into the horrible territory when n is squared 2 to the exponent of n. Over here you would have n cubed. N cubed is even worse than 2 to the n in terms of operational performance. This is something you can memorize. I have 2 different charts here you can look at, you can go through. So for the big O, a big O of 1, that's called a constant, which is exactly what we'd have. This is going to be whatever. If it's a, big O is 10, then it's going to be 10. That's going to be the constant number. Log of n, logarithmic and linear. We saw that log of n and the constant and the O and linear, they're pretty fair in terms of as your elements grow, as your n grows, your operational computation intensive doesn't grow substantially. That it's still considered a valid function, a valid formula you're going to be using. And then we go n log linear. We're getting into that, what was that, fair? No, bad. So we left fair, we're in bad territory already, just because of the amount of computational intensive that is putting on the system, regardless of your system. And then we have n squared, n to the third, and then we have 2n in terms of quad, cubic, exponential. So this is just things you can start to memorize, and what you're going to be doing is this is what we're looking at when we're determining our function. Where does it fall in terms of the big O? This is a more broken down version of the big O, showing our 1 log of log n log n and so on and so forth going, and this to what their actual functional name is going to be called if you were ever describing it. What I have here, this code, I'm not going to go through per se. I'm just using this for demonstration purpose. But we're importing log, importing numpy, importing matplotlib. I'm going to have matplotlib in line, which you're going to see in a moment. Setting up runtime comparisons. So what we're doing is we're using numpy to create a line space 1 to 10, and then we're giving it different labels: constant, log linear, quadratic, cubic, exponential. And then what we're telling it to do here is the actual calculations. Each one of these calculations is corresponding to its particular label. So therefore this could have been done even like a dictionary if you were going to do key values. And then we're just setting up our figure size, and we're going to be plotting it. And then this is how we're actually going to go through the calculation piece. What I'm going to do is go through that, and here we go. So what this is, just another graph version showing you that the n increases with the relative runtime on a particular system. So in this case, this is my system, and it's giving you a color code below that we're constant, log linear, quadratic, cubic, exponential. So again, you can see we're in good, better, worse, and then just asinine territory. So even with an n of 4, you can see the relative runtime performance. So here, when we're in constant and log, so we have constant log at 4, our relative runtime is, you could say that's like 1 and change. And then once we start to get up to linear, log linear, even with the n of 4, we're still under 10 for relative runtime. So it's not crazy. These guys can be somewhat grouped together. But now we're launching out of the territory here with quad, cubic, exponential. Even with the n of 4, we're hitting relative runtime substantially. And look, with an n of 4, we're looking to go off for relative runtime here, even for a cubic, and we're out of the ballpark. And what did we find for cubic was that's exactly what this big O notation was for this particular, it was cubic run. So its big O was cubic, so in terms of its relative performance, you could see with a small n, With an n of 1 and n of 2, we saw a substantial change. Then n of 10, it just skyrocketed. So we're here with an n of 10. You can see how the relative runtime, if we ever even get up to the cubic, it just rises at exponential. It rises at a cubic rate. So clearly, we want to choose algorithms to stay away from any exponential, quad, or cubic behavior. In terms of computational intensive, typically mathematics, and you're going to see this when we're doing machine learning and AI, and we will do exponential, quadratic, cubic behaviors, but we don't want to be doing them on large scales. So if we're going to be doing them, we want our n's to be relatively smaller. So if we keep our n's small, we can keep our relative runtime in a manageable fashion. But again, this is exactly why if you're running certain neural networks on particular models on different PCs, why you can have runtimes that go hours, days into weeks, depending on your system, and why things like the GPU and its parallelism, why it has such a massive impact on decreasing the amount of time that we can run with ML, AI, and DL. And even something you're going to see soon coming out, which is the NVIDIA Volta. Well, it's already out. One of the biggest pieces of that is its ability with tensors. And when you have a GPU that is primarily focused on tensor mathematics and manipulation, you're going to find that the scaling of that is going to be astronomical, and the speed of that is going to be a heck of a lot faster than what we currently have, even with, say, the Titan XP running up with Pascal. So that's going to be it for today. Again, this was beginning of algorithms, and we start with a big O notation. So, and this information that we're doing now is not just for, like, say, for computer science, and it's not just for your own knowledge. All of this is, even if you start going to interviews for computer science, you're going to be dealing with functions or formulas that are going to be looking, where are they falling in this? Are they computationally intensive from a memory standpoint or from a time standpoint? How could you make them better? What could happen that could make them worse? And how can you make them functional in terms of what they're doing? Because again, you can code an incredible piece of code, but if it can't be run on 70% of systems in the world, then what good was the code? So you have to keep these things somewhat logical. Big O examples. First, for a big O of 1, a constant number. So we have here creating a function. Function is constant. We're going to put values as the argument. All we're doing is printing, in this case, the first item in a list of values. How do we know it's the first item? Because we're indexing at 0. It's going to be our first item. So we're printing out values, whatever we're going to run through values as the argument, and printing out the index of 1. So we're calling that function here function constant 1, 2, and 3. So out of this list, that was what we're passing through our function of function constant, give me the index position of 0. And sure enough, it gives me 1, because that's appropriate. Now, the point of this is that it doesn't matter how large my values list becomes. This values list, I could have made this and I'm still going to get 1, because it doesn't matter if this was infinity digits long, I'm only grabbing the first index position, which is always going to be 1, and it's also in the first spot. So this algorithm is only going to grab the index position 0 in that list, no matter how many times I run it, no matter how big this list is. So this is a constant. This is a big O of 1. And constants, as you remember from the chart from yesterday, have one of the lowest computationally intensive impacts on a computer system in terms of performance. So scalability, this is nothing. This is easy as balls. You could scale this as much as you want. We're only grabbing the first index position. So now we're going to move on to O n, big O of n, which of course is going to be linear. It's not a constant, it's linear. So linear is slightly above in terms of we're still in good performance on a big O performance chart. So regardless of n, we still can get fair computational intensive out of the system. So here we're defining a function, and we're going to put a list through there. So we have for val in list, so that's going to be for our values in a list. We want to print the values. So it doesn't matter what our list is going to be, it's simply going to print this. You know what I'm going to do? Let me do this just so you guys can see the outputs as we run it, so I don't want you to feel like your brain is cheating. So here I'm going to pass the list of 1, 2, and 3 through my function list defined function, and all it should do is print out each one of these values within the list. So we're going to shift through there. So of course it prints out 1, 2, and 3. So for every value is going to print in the list. Each time the list gets larger, though, what's going to happen to our O(n), it's also going to get larger. It's not going to be a constant. It's going to be linear. So if right now, if it's 3, it's going to print out 3. Conversely, if it was larger, it would print out a larger list. So our list growth does have an impact on the computational intensive of our system, and it has a computational intensive risk of, so you'd say big O to the n. It has a linear growth rate. So as our list grows with this particular function, as our list grows, so too does the computational. Not to the point that it's disastrous, though, because again, computers can do a hell of a lot of math. But again, the point is it has to do the whole list, whatever I do pass through here. So that's why O(n) linear is going to be a little bit more computationally intensive than O(1) constant. So what do we have? Every value will print the list each time, so the larger the list gets, the bigger the big O. Yeah, that's exactly what we just covered. So now we're going to go to quadratic. So this is going to be O with n is squared. So we're going to create a quadratic big O function. So in this case, we're going to do that just by doing a for loop in a for loop. So we're going to do a functional quad. We're going to have a list. And what we want to do is print a pair. So for item 1 in list, and then for item 2 in list, print item 1, print item 2. Nothing crazy. We'll make our list just for fun. We'll make it a little bit bigger. I want this to be neat. And then we're just going to call our function quad, and then put our list through our list that we produce of 1, 2, 3, 4, 5, 6. So what this is going to do, it's going to go for item number 1 in the list, and then it's going to print 1, it's going to print 2, it's going to print 3, it's going to be 1, 1, 1, 2, 1, 3, 1, 4, and it's going to do this for each item in the list as it goes through list 1 and list 2. So sure enough, we have 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3. We're never dropping anything off. 3, 1, 3, so it's creating a pairs list all the way through this. But the point of the matter is that this is going to be one iteration for the computer system. For number 1, let's just take one element within our list. So for the first element, it has to do this run, and then it has to do this run. So it has to do n times n for each element that's in our list. But this doesn't matter how big this is. It doesn't matter if this is one number or one element. It doesn't matter if it's a million elements, infinity elements. The point is it's always going to have to do n times n. So that's how we're getting our n squared. That's going to result in this. That's exactly what we're getting from. We're going to have a quadratic representation of this on the graph, which, as we saw from last week. Let me bring that up. When we get into quadratic, again, we can see that as the elements grow very quickly, let's say, we're at 0 and then 1 and then 2, as our elements grow, as our n grows, the operations are going to be, in this case, exponential, because we're n squared. It's because we have 2 loops, one less inside the other, as we said. For a list of n items, we also perform n operations for every item in the list. That means the total will perform of n times n assignments, or n squared. So if we have 3 assignments, let me show you. So if we only have, here we have 6, so we should have 36. So if you counted this down, 1, 2, whoops, you should have 36. So let's keep this a little shorter so it's easier to see. So if we have 3 elements, we should have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's our n times n, or n squared. Whatever our n is, it's going to be n squared in terms of the computational intensive for that particular system. How many operations are we actually performing? We're performing this n operations for n operations in a loop of loops. And it says you can see how very dangerous this can be for very large inputs. This is why big O is so important to be aware of when you're creating software. Hence, the input of 3 gives us 9 outputs. That's what I just showed above. We have 9 outputs for an n of 3. Calculating scale of big O. So insignificant terms drop out of the big O notation. And this is exactly what we saw yesterday when we did... Nope. Here we go. In terms of, these are called insignificant terms, the 45, the 20, the 19, but you're always going to go in a backwards order, meaning that the lowest term is going to be the 19, and then it's going to be our square, and then it's going to be our cube, in the terms of the constant that stands before them. So as you saw, just going from a big O of 1 to a big O of 2, our 19 started to become very insignificant. And then from a big O of 2 to 10, not only did our 19 become insignificant, but so too did our 20 and our 45. What came significant, though, was the cubic. Even our square started to show that it was falling off rather quickly. So as the n increased, that n squared is going to become smaller and smaller compared to what the cube is going to contribute to the ultimate outcome of your answer. So when it comes to the big O notation, we only care about the most significant terms. Remember, as the input grows larger, only the fastest growing term will matter. This is, again, like taking the limits toward infinity if you're familiar with calculus. So that's what we always want to focus on. What is the most significant term? And that's what we were hitting on here. Out of this whole function, this is the most significant term, because as n grows, this is going to contribute the largest to the overall answer, in proportionate to the other values that would reside within that function. So here we're creating a new function to find print once, and it's going to print all the items once. So for the values, or for a val in list, print the val, print list, print once, and then we're just going to call our list. So what list is this? Well, it's going to go by our last list that we ran in the Jupyter Notebook, so it's going to be list 1, 2, and 3. So if you wanted to see that, you could also run it. It's going to print the list 1, 2, and 3. So we can see how the growth is linear for this particular input. So this is just going to be, since it's a linear growth, it's going to be big O to the n. And you'd say, yeah, that makes sense, right? For every value in the list, if there's 3, we're only running this n times. If n is 1, we're going through this once. If n is 2, we're going through it twice. If n is 3, we're going through it 3 times. So it's a linear growth rate for the function that we're dealing with in regards to big O. Here we're defining print 3. We have our list, but now what we're doing is we're printing it 3 times. So for each value that's in our list, we're doing it 3 times for each particular n. So for our list, it goes through print value in the list, it's going to be 1. Print value in the list, 2, 3, 1, 2, 3, 1, 2, 3. It's just printing this 3 times because, again, that we have 3 different for loops within our function there. So again, this is going to run 3 times for each of the n's. This becomes an order of 3 times n. Now notice it's still linear. It doesn't automatically become n cubed. That wouldn't make any sense because each of these are going to be run in a sequential fashion, so it's just going to be 3n, but it's still linear. The important thing here is this. 3 times infinity is not really different than infinity, so we can drop the insignificant constants, and that's why this 3n, you'd be technically correct to say this is a big O of 3 to the n. As n grows, our computational tensor is going to be 3 times that n. However, as n becomes infinity, the 3 becomes inconsequential, becomes an insignificant constant. So this would be a big O of n. So this is no different than this would be in terms of its big O notation. Granted, would you say this is going to run faster than this? Absolutely. But we're talking very small lists right now. When we get to very, very large lists, those times this should still always be longer than this, but it becomes inconsequential in terms of the difference. And here we have a new function. We're defining the comp. It's going to take a list as an argument. So now we're doing 3 different things, and you can ignore this right now. Let's just go down and see what we're doing. So we're printing the list of the first position. That's all we're doing first. And then we're creating a new variable called the midpoint. We're going to take the length of that list and divide it by 2. And then we're taking a for loop for the values in the list from the beginning to the midpoint. Print that value, and then for x in range 10, so we're going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, print the number. So I'm going to shift enter through that so it can actually create its part. Auto saving. Oh, Jesus Christ, I never called. I'm like, why is it running? I never called my actual function that we created. So here I have my list. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm calling the function we just wrote up above. And I'm passing through this variable. So now we have 1, 1, 2, 3, 4, 5, and then we have the word number printed 10 times. So what is the big O of this particular function? So if we're looking through this, again, you might recall this from yesterday, all we're doing here is taking our list that we have here and pulling out the first indexed position. That's going to be a constant of 1 always, right? It's our big O of 1. That's a constant. That's what we have here. This first function is going to print a big O of 1. This is going to be a constant, nothing special there. This is just creating the variable midpoint. We're taking a length of the first, dividing by 2, and then we're using that in this piece here. So what we're doing is, all we're doing is printing the first half of the list. So we're from the beginning of the list to the midpoint, print those values. So if a list of 1, 2, 3, so the midpoint you're going to tell me is going to be 5. So go from the beginning, because it's 10 divided by 2 is 5, and then go from the beginning of the list to the midpoint, it's going to print 1 through 5. That's what it's going to do for this point. So for this one, this is going to be, that's what we have here. We're only doing half the list. So it's big O n divided by 2. Because whatever my n is, here my n was 10. So the big O is n divided by 2, it's 5, because we're going to have an output of 5 different elements. And then for the last one, for x in range 10, so we have a constant here, right? Doesn't matter what this is, constant, all we're doing is printing in numbers. This is going to be O to the 10 to big O of 10, or a big O constant. So what we have here, we have O1 constant, we have O n over 2, and then we have big O 10, which is also a constant. If we were to compare all three of these, that's what we're doing down here, we have big O1 plus n over 2 plus 10. What did we say, though, about constants? Constants are going to fall out as the n gets larger and larger and larger. As we're scaling up, you're going to see how the number 1 and the number 10 are going to quickly mean absolutely nothing to our overall answer for computational intensive on a big O. And even the divided by 2 is going to begin to have no effect either. So what we're going to be ending up with is a big O of n. This is also going to become a linear growth rate based on the n, because the constants, though they do have a mathematical impact early on, that impact falls off dramatically as we scale up. So another piece that we're going to speak about when we get to big O is, and talk big O notation in computational intensives and algorithms, is worst case versus best case. Now, there's no point in really computing a best case other than knowing what your best case could possibly be. But it's best to do your big O notation in a worst case scenario. So that's why we're usually concerned with the worst possible case of an algorithm, because then you know what your worst case scenario is going to be and you can work up from there. But in an interview setting, it's important to keep in mind that there is a worst case and a best case scenario, and they can have very completely different big O times. They should have very completely different big O times. So what we're going to do here is we're going to create a best case scenario first off. So I'm going to create a function. I'm going to call it matcher. It's going to take a list and it's going to take a match. So we're having two different arguments that are going to pass through this function. And then for item in list, for item, if item equals match, return true. Otherwise, we're going to return false. We're going to follow the loop. So I'm going to have a list. We already have a list produced. I have LST here. I'm just going to run this cell to see what our list is. So it gives me the output. Our list is 1 through 10. All right, sweet. And then what I'm doing here is I'm calling the function which created a matcher. And I'm saying for the first argument, it's list. So that's what I'm putting through here is list. And I'm putting a number 1, so a match of 1. So what it's going to do is going to say for item in list, for number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if item, if this equals the match, and the match here, that was our argument. Here's match, here's my argument. If any one of these equals this, it's going to return true. Otherwise, return false. So it doesn't say, it says if any item, essentially is what we're doing in that list. So what do you think we're going to get for this one here? Well, we're going to run it. We're going to get true, because sure enough, within this list, there is a match for the number 1. Now, the reason that this is a best case scenario is because where is the number 1 that we're trying to match? It's in the index position of 0. It's at the very, very first of our list. So a computer is going to go sequentially when it's dealing with a list. Or, when we get to different kind of algorithms, you can see, you could say, we could split it, we could do higher, lower, and go from there and just break it down half and half and half and half. But in this particular example, our list, what we're matching is the first element. So the list goes, is number 1? Yep, true. That's our bet. So the time to compute that is very, very low. Now, in terms of a false, we're just going to run a code to make sure it's working. So we have our list. We're passing a 20. There is no number 20 within our list. So we're going to get a false. Now, this is essentially technically a worst case scenario, because in order to find out if this was true or false, in order to make this part of the code to determine if we were going to fall down into the true or if we were going to jump out of the loop and return false, the computer had to go number 1, and then it had to go 2, 3, 4, had to sequentially go down this list to find that there's no number 20. So in the first run, matcher first 1, we only had to go through an element of 1 to find the true. In matcher list 20, we had to go through 10 different elements to find out that it's false. So technically this is a worst case scenario, because we have to go through our entire data set to find out that there's no match. So that's a worst case, because again, the entire list must be searched, n elements, O to the n, worst case becomes linear. This is a big O of 1, the constant, because again, 1's always going to be in the first index position within this particular list. Lastly, we're just going to talk on space complexity. So not only did we talk about how obviously there's a huge time complexity with big O notation and functions and algorithms, but there's also a space complexity. It's also concerned with how much memory space an algorithm uses. If you ever tried to do data work with AI, ML, DL on images, on ImageNet, or in any particular Kaggle piece, if you have a crappy GPU, it's going to come out and say memory error, because you're trying to allocate, the algorithm is trying to allocate a certain amount of memory to the problem, which it does not exist. So it's telling you, I can't run this crap because you need more memory than what you have. So this notation of space complexity is the same, but instead of checking the time of the operations, we're checking the size of the allocation of memory. So in this quick example, we're just creating a function called memory, and we're putting it n equals 10. So then if we look at the code, it says for x in range n, again, n was 10, we're going to print memory. So we're going to print the word, the string memory. So then we call memory 10. What's going to be our arguments? Actually, let me take that out, because we assigned 10 to our argument of n when we ran the code. So of course, very complex code, right? It's going to print the word memory 10 times. But if you're looking at this loop, what we have here is this first piece is a time complexity, because if n is 3, then it's going to run through this 3 times. If n is infinity, it's going to run through this infinity times. This is a time complexity. So this is O to the n, because as n grows, so too will the time. This is a linear growth rate here. It's only one element, it's only one operation to run through to make that sufficient. Now for print memory, this is going to become a space complexity. And we have a big O of 1 for space complexity, because memory is a constant, meaning that it's not printing, it's not creating 10 versions of this, it's creating it once, and in terms of space complexity, it's just creating our one constant, it's running it 10 times. But the point is, this is the lowest computational intensive that we can deal with, because it doesn't matter if I made this as 100 and ran it. I'm not going to read through that for you, but it's not going to have any kind of effect on the big O in regards to space complexity, but will have effect of time complexity. So we have O to the n for the time complexity, which we already came to that conclusion. And the space complexity in memory, it doesn't need to store 10 versions of memory. It only needs to store one string, and that's going to be the constant. So again, in terms of if you said which one of these is more efficient, you would say the constant is more efficient than the time complexity. So in this particular code, if you were dealing with a larger piece of code and you had time complexities and space complexities, and if you had a space complexity of big O to the 1 and time complexity of big O to the n, if you had to manipulate some aspect of the code or to store something, you'd rather do it from a space complexity standpoint, because the computational intensive of that from the big O of a constant is much lower in terms of scalability and in terms of limits than the time complexity of big O n, because this, even though it's still linear, this is going to grow at a much faster growth rate in terms of computational intensive than the space complexity of a constant would. Now again, I don't expect all of this to sit within the first time that we're doing this, but that's why you have videos. You can go back and do this again and again, and we're just going to have more and more examples. And the whole point of this, again, was for algorithms, for also playing with Jupyter Notebook, but more so for algorithms, and then even doing with interviews, because as we get into ML and DL and AI, a lot of that is algorithm-based. And even if you're doing something with NumPy or Pandas or Scikit or sklearn, it's important that you understand what that algorithm is doing just from a complexity standpoint. So as you grow and you're trying to scale things, and if you're hitting limits or walls, you'll know what those limits or walls are caused from. So in Python with array sequences, there are 3 different types of arrays. You can have a list array, a tuple, and a string. Now these are all different 3 types of arrays. You can see that the list is going to be identified by the brackets, a tuple, parentheses with a comma in between them, and then a string is identified in between parentheses with the quotations. What makes all 3 of these unique in terms of an array sequence is all 3 of these can be manipulated by indexing. They all support different indexing parameters. So to quickly understand some of the basic theory before we get into even the interview question, to understand how arrays work, we need to understand low-level computer architecture. So what I have here is a memory. Assume this is like your RAM, your random accessible memory within the computer, and each one of these numbers, 2144, 2145, 46, etc., are like address locations. Now memory is stored in bits, but 8 bits is a byte, so we go by bytes when we're looking at this data. And then there's a memory address for each byte. So in this one byte here, 2144, it actually has 8 bits within it. That's how we're visualizing this. Now, what's interesting about, at least with the arrays, is that they're stored and retrieved in big O1. It's a constant time, so it does not matter if you're at the beginning of an array, middle of an array, at the end of the array. If you're indexing its position anywhere along this memory sequence, the big O, the time, is going to be constant regardless of where you're doing it. And again, this is theoretical, but it's also pretty much in practice. So the idea is no matter how much you have stored in memory, if you're using indexing, you can recall it in the same amount of time, regardless of if you're using a list, a tuple, or a string. And also regardless of its indexing position. So if you have a book that's all in one string, if you're indexing the very beginning of it or the very end of it, it's going to be able to have the same kind of a recall time because of its memory address location. Python is represented in Unicode characters with 16 bits. And again, if there's 8 bits in a byte, then 16 bits can be 2 bytes. So in 2146, 2147, if we had the string sample, it would show me an index of 0 in that string is going to have the element S for sample, and it's going to take up 2 bytes within this memory sequence, address 2146, 2147. So if I index 0 or if I index 3, the Python is going to know exactly where in the memory, what address to go to actually recall that element that resides within that list, tuple, or string. So we have sample is 6 characters. It's going to be 12 bytes because, again, it's 16 bytes for 2 bits. 16 bits for 2 bytes, sorry. We have an array here of 6 characters, 1, 2, 3, 4, 5, 6, indexing 0 to 5. Each character is going to take up a cell. So this cell S is actually being composed of 2 different bytes. And then the index describes the location. Of course, 0, 1, 2, 3, 4, 5 is describing our location of our string, tuple, or list. And this is just for knowledge. We're going to be using, the work that we do is going to be higher level abstraction. This is considered low level abstraction, the very lowest level you can get into in terms of arrays. So quickly talking about lists and references. So looking at this image here, assuming we create a list and we named it primes, and it's storing the prime numbers, 2, 3, 5. We created this list, and it's storing it within these index locations here within memory. So now you know that index of 0, 1, 2, 3 is actually going to correspond to a physical address within the memory in the computer. These are the reference points that it's going to have. Now assume we create a new list. Say we had like a temp list, and we wanted to reference a portion of the list, like if you were splicing a list. The point is, it's not going to create a brand new list. All it does is it takes the temporary list that you created here and it just changes the index assignment of that list to reflect where those elements are within memory. So down here we have, if you want to change an index assignment to a new temp list, say we did temp index of 2, 0, 1, 2, so that's this location here of 13. Right now it's pointing to 13 within the previous list of primes. All it's doing is referencing primes index of 5, which is at 13. It's just indexing. Now temp 2 is indexing at 13. It's just referencing that particular element within stored memory. If we want to change it to 15, the original list is not going to change. All that's going to happen is right here, this 2 right now is referencing 13. This 2 will then point over here and reference number 15. It's not going to actually change. It's not going to append or amend this list that exists within primes. It's just going to change its pointer. And that takes us to a topic called pointers in regards to memory, and very crucial at the low-level aspect of understanding computer science and how things are stored in memory and recalled and referenced. But the important thing here is that the original list is not changed. 2, 3, 5, 7, 11, 13, 17, 19. That's not changed. If I change this temp index 2 to 15, it just comes over here and references a different location in memory that's storing the 15. It does not mess with the original list. So we have here the takeaway is new list, create a shallow copy, meaning you're only changing or creating your pointers. You're not duplicating objects in memory. And much of what we're doing is manipulating references and calls, not the object itself. We're manipulating the reference and the calling of the elements. We're not actually changing the physical object that resides within memory. So quick little exercise here. We're importing sys. It's a module within Python. Creating n equals 10 data is an object that we're creating with just an empty list. And then for I in range n, again, n is right now 10, so it's going to be for 1, for 2, for 3, for 5, and it's going to go through this. A is a variable that we're just saying, give me the length of the data. At that point, data, again, right now is an empty list, so at the first point, it's going to say 0. B equals sys.getSizeOf. GetSizeOf is a method that resides in the sys module. And we're saying, give me the size of data. and then I'm printing on the bottom here, we have a string that says length. Now this, it looks like a dictionary, right? It looks almost like a key value pair that we have here. But what this is this is string formatting. And what I'm going to be doing is, if you see this and then look at this. So what this is saying here is at index 0 of format, so dot format index of 0 is going to be A. And A is going to reference this data. So it's saying, I want you to put length, colon, and then I want you to give me the value of A. And I want you to only take 3 integer places. That's all that's messing with right there. And then size in bytes, index of 1, which is going to be the value of B. B is generated here. And we're saying give me B and take that 4 integer places. Now you'll notice you can also do left and right alignment. So if we're calling for 3 integer places and we only have 1 number, you're going to have 2 and 1 left of it, because it's going to automatically default to right alignment. But that's what this dot format method is. I'm saying dot format A into this position, 0, and format B into this position here when I print my string out. So data.append n, again, this is just saying with my empty list here, append it with the number n. So right now it's empty, we're going to fill it up. So I will run this cell, even though I already have a run down below. And I just want to quickly go through what this means. So a length of 0, because the original data is going to be 0, the length of data starts off as 0. Python automatically reserves 64 bytes in memory, even though the length of the list has not changed yet. And I'm going to bring this down so we can see this image down here. When it goes to length of 1, the size in bytes does go up to 96, but then with the length of 2, the size is still 96. 3, we're still 96. 4, we're still 96. Once we get to 5 elements within our list, now we go up to 128. Python is increasing, and then it runs at 128, 1, 2, 3, 4 instances before it runs up to 92. What is this doing? The point of this is that Python, we don't have to dictate the size of the array before we create it in Python. It's going to grab a little bit more memory than what it's going to need, and it's going to fill up that memory. And when it gets to the point of where it can't fill up anymore, it's going to create a new sized array. It's going to copy over the previous array, and then it's going to almost double what it's doing. Depends on your byte size. So down here, if you have this array that has 4 elements, 1, 2, 3, and 4. So if our length of 0, 1, 2, 3, we're good. But then once we start to get to 4, 5, 6, it's going to have to jump down to a new size array. So that's what we're showing here with B. So B is an empty array, and it's going to take the elements of A, because B is bigger than A. It's going to take all the elements of A, and it's going to point them to B. So here's our elements. Here's our elements. First, A is referencing. Now B is also referencing. And then A is going to become garbage. B, what was B, is going to hold those elements, and it has more spaces here now to take on more elements, more appending of that particular array. And you can see it just changed the assignment to A because this became a garbage array, which we'll get into another time. But the point is, you could even make this whatever the heck you want, and you can just see that it's gonna create a new size, and it's gonna hold it as long as it can, and then it's going to move that array into a larger array of memory so that it can hold those points, but it's not point for point. It will hold it for a certain number of time, and as the length increases, then it will jump to the appropriate size of memory, of course, until you get a memory error. All right, guys, that's it for today on the array sequencing. Again, we have list, tuples, and strings. They all support indexing. That's one of the main takeaways there. Then we just did some low-level pieces of memory recall and data storing for arrays, and just showing you how exactly those things are stored and how we can jump through how Python can increase its memory size of arrays if necessary. Any of your questions for me are things that you should pretty much kind of sort of have memorized. One, for the point of recall, but two, memorizing code does have a huge impact in terms of if you have to utilize code later on. You can always recall it, of course, but also you can use parts of code when you're building new pieces. So this is just for dynamic arrays interview questions. And we're going to have a couple of interview questions for arrays as we go through this work. So the problem you're given, we're given two different strings. We want to see if they are anagrams. So an anagram is just when two strings, or two words or a sentence, if both of them can be written using exactly the same letters. No repeats in terms of, you can't have one that has 7 A's and one that has 8 A's, but they don't have the same letters throughout the entire sentence, phrase, or word. All you have to do is rearrange the letters to get a different phrase or word. So for example, public relations is an anagram because I can take all of the letters of public relations and I can create crap built on lies. Isn't that ironic? Public relations crap. Anyway, so without having to increase or decrease any amount of letters, the spaces don't matter. So it's just about the letters. Clint Eastwood, those letters can be rearranged to make Old West action. So we want to build a software. We want to create a function rather that will take in a string and 2 strings as arguments and compare them to see are they anagrams. We want to ignore spaces and capitalization, and that's pretty easy to do. So again, D space G-O is an anagram for God, ignoring the capitalization, ignoring the space here. So we're going to do 2 different solutions for this. The first one we're going to do in Jupyter Notebooks, and the next one we're going to do in PyCharm. So for the first one here, we're creating, and I'll explain to you why we're doing 2. We're creating the function anagram, and we're taking in 2 arguments, S1 and S2. And the first thing we want to do is we want to tell Python whatever string we give it for S1 and whatever string we give it for S2, first and foremost, get rid of the spaces. So S1 equals S1.replace. So this is a method that exists within Python. We want to replace spaces. There's a space here. I'll show you. I'm going to take it away, and I'll put it back. Replace spaces with no spaces and lowercase everything. And we want to do the same thing for the second string. S2 equals S2.replace, take all your spaces, get rid of your spaces, and lowercase everything. Wonderful. Then all we're doing is we're going to return a Boolean for a sorted match. Sorted essentially putting them, alphabetical order or numerical order. So if the letters in S1 can also be used to make something else in S2, then they would have the same letters. So if they're sorted, they should be equal. So return sorted S1 equals sorted S2. It's either going to be true or false. So when we run it, first we're going to call our function, anagram, that we made above, and taking our 2 arguments, first dog and then God, and we run it, and sure enough, it's going to tell us true, and that is correct. Same thing for Clint Eastwood, old action. We're going to run it, true, and then we get a false here for anagram AABB. Why? They have the same number of letters, absolutely 2 and 2, but you can't make BB from AA, or vice versa. Conversely, if we made this a capital T, it would still give me a true because we are lowercasing our letters. If I added one more letter, I do get a false because now it's saying you can make Old West action from Clint Eastwood, but now you have a U here, so we have a letter that's left over that Old West action did not use. So it is not an anagram in that example. Now we can make it back to an anagram. This is not an optimal solution for an interview because you're using a Python module. We're using .replace here. And I don't want to say it's cheating, but if your interview was if it was in Java or JavaScript, if it was in a different language, C++, you're not going to be using Python modules. And so you want to be able to also do this anagram solution using counts and dictionaries. And that's exactly what we're going to be doing in PyCharm here. So I'm going to run through the code, and then we'll actually run it, and you'll be able to see what it's doing. So we're defining anagram 2, again, same 2 arguments, S1 and S2, and we're doing the same thing in the beginning. We're taking S1, and we're doing S1.replace. We want to get rid of the spaces and replace it with no spaces, and also lowercase everything. Same thing for S2. S2.replace, get rid of the spaces, no spaces, lowercase everything. Then what we want to do is we want to check if we have the same number of letters in each of the strings. If we have the same number of letters, that's a start. If we do not have the same number of letters, then we know off the bat we do not have an anagram. So if the length of S1 does not equal the length of S2, return false. And that's exactly what we want to be able to do. Because again, if it was going to be true, if they did not equal each other was true, then that means one string has, say, 13, the other one has 16. It can't be anagrams. So if they do not equal each other, return false. Then we can keep rolling through. So count frequency of each letter. Count, we're just having as an empty dictionary. You'll notice our brackets there. So we have an empty dictionary for count. And now we're saying we're going to create a for loop for letter in S1. And I'm going to actually do debug through this so it makes more sense for you. For letter in string 1, for every letter in the first string, if letter in count, count's going to start off as 0, but if the letter is already in the dictionary, then I want you to add a 1 to that count for that. So if it's going to be like a key value, so if the first letter in Clint Eastwood is C, we're going to start out with a 0. So then I want to make that C equal 1. else count is just going to equal 1 if it's not already within the dictionary that we created here, which is empty at this point. And then we're going to do the reverse for the second string. The reverse meaning we're going to subtract. That's all we did here was change the plus over before to a subtraction now. We want to subtract 1. So we want to count all the letters up and then bring them on back down. And then at the end here, we're just saying for k in count, if count k does not equal 0, return false, because every letter should equal 0 after we count up and then count down. And then lastly, if all of this is met, for this function, you can see how we're doing our indenting, we can return true. And then I just have here x equals anagram 2, Clint Eastwood, Old West action. You can see I capitalized West, I capitalized C and E. Well, we already know from the previous example that these are anagrams. Then we're going to print x and see if we get a true or a false. So what I'm going to do is I'm going to come up here, debug it, and we're going to run our debug. Yes, for anagram. And I don't care about that. We're going to go console for now. So, bring this down a little bit. So it's a little bit, all right, sweet. All right, so I'm going to come to the first line and we're going to F8 through this. So again, you can see we went from line 1 to line 32 because when we're debugging, it doesn't go through a function until the function gets called. So here in the variable x, we're calling the function anagram 2 and we're giving it 2 arguments, S1 and S2, Clint Eastwood and Old West action. So now we can actually run through our function and you can see here, it put into memory S1 Clint Eastwood, into memory S2 Old West action, and you can see it maintained the capitalization so far because we didn't do anything with the code. F8, so now we can be within the function because we have our arguments. S1 equals S1.replace, so it should, if you're looking at S1, watch S1 as I F8 through this. You're ready, set, go. So you can see that it got rid of the capitalized C, the capital E, and it got rid of the space. And it should do the same thing now for S2, and go. Old West action. Great, so now we have 2 strings that are both lowercase and no spaces within them. Now we want to check if we have the same number of letters. So let's see what happens. We're going to F8 through this, and it jumped from if length does not equal return false, and then go down to count. So this went through. This did not meet the requirement, so it jumped down to the next piece because they do equal each other. So count equals an empty dictionary. So let's F8 through that, and sure enough in memory, it creates an empty dictionary. How lovely. And now we're going to go through our actual, bring this up a little bit so you can see it better. Now we're going to go through our actual S1, which was Clint Eastwood, no capitals and no spaces. So I'm going to F8, and you can see it gives me right off the bat a letter C. And we're going to F8 through here. It gave me the letter C, so it said if letter in count, which it was not, because C was not in count, count was empty. So letter C was in count, nope, so it's going to jump down to else. Count equals 1. So watch what's going to happen here to count. Once I F8 through the next line of code for count letter equals 1, bam. Now we're creating in the dictionary the key C, a value of 1. Now if I come across any more C's, that C is going to turn into 2 because then it's going to say if letter in count, yeah, C's in count, letter equals 1 plus 1 at that point, it would be 2. So now it's going to go through each letter. So first C, then we're going to see L. So we're going to F8 through this, and sure enough, it tells you over here, letter is now L. If letter is in count, L is not in count because we can see in count we only have C. So then it's going to jump to the else, which is the count letter equals 1, and we're going to have in our dictionary up above, L and 1. So I'm just going to go through this, I, N, T, E, A, S. Now, we already had a T. So when it got to east, E-A-S-T, it did not create a new key value, it changed T to number 2, because now we had 2 instances. Let me drag this over a little bit. How do I do? I can do no, it's active editor, right? Use soft wraps. Give me soft wraps. O D D. I didn't want to go into S2 yet. So it was Clint Eastwood, and it didn't do Old West action yet. So we got to Clint Eastwood, and that's what it did. Eastwood, Clint Eastwood. E-A-S-T-W-O-O, O is 2, that's why, and then D. All right, and now it just brought in the letter O, and that's the beginning of our second string. So all we did so far was, in this for loop, in our count, this empty dictionary, we now have a filled dictionary with a key value for all the letters in Clint Eastwood. Now in this second for loop here, it's going to do the opposite. Now it's going to go through Old West, and it's going to say, is there an O if the letter is in count? Is O in count? Well, yeah, we have 2 O's in count from before, so it's going to go -1. If it didn't exist, then it would do a 1. So the idea is all of these should be 0 by the time we're done with going through Old West action. We can see there's 2 T's in Old West action, and we have 2 T's in Clint Eastwood, so it should go down. So I'm just going to, again, start F8ing through this, and you can see up here, if you watch up here as I F8 through all of this, you're going to see all of these numbers go down one by one until they all get to 0. And it's not that they're all going through 0. The variable on line 12 is also changing each time we go through the loop. Now they all came through on 0. We went through all the letters in S2, and we can see that they're all 0. But that doesn't mean anything yet for the code, because now it's going to do for K and count. K for C. If K count does not equal 0, return false. So we know that all of our K's in count are going to equal 0, 0, 0, 0, 0, which means it's going to jump out of this loop and return true. So it's just going to go through N, T, E, A, and it's going to go through every letter within our count. And you see here in memory, X is true. F8 through it, print X, and we can see, I'll bring it up for you. You can see in our console, it printed out true. So now we know that it is an anagram. Now I know that seemed a little, normally when you're doing this, you're not going to be debugging through it, but I wanted to, let me get rid of that so you can see the line better. I should change that highlighting. I wanted to show you the code and debug through it so you can see again what's happening in memory when we're creating an empty dictionary, adding to the count based on a key value, and then deleting from that count. So this way, no matter what language you were doing this in, you could do the same kind of a process to check if something was an anagram or not. Also good exercise with for loops, indentation, the replace method, and lowercase. Always good practice. We have another coding example that we're going to go through and essentially utterly memorize so that we have more tools within our toolbox. So today for array pair sum, excuse me, that's what we're going to be dealing with. So again, for arrays, you could have list, tuples, or dictionaries. Those are all different kinds of arrays we're going to be utilizing, but this is going to be array pair sum. So given an integer array, so say we have an array of 1, 3, 2, 2, which you can see down here that I've already defined in pair sum. Given an array, an integer array, 1, 3, 2, 2, output all the unique pairs, the pairs of these integers, that can sum up to a specific value of k. So that can sum up to a specific value of 4. So our input, we're going to make a function called pair sum. We're going to pass through argument 1, which is going to be the array, and then argument 2, which is going to be the value of k, or some kind of specific sum that we want these to see if we have any pairs that add up to. So in this case, if we ran this, if we have our function done properly, it should return 2 different pairs, 1, 3, and 2, 2. Because 1, 3 adds up to 4, 2, 2 adds up to 4. And 1, 3, and 2, 2 are integer pairs that were within the array that we're passing through. So let's get coding. First off, we need to define our function. And like I said, we're passing through it an array and a value of k. That's going to be our first piece there. Now, before we even get into anything, we want to make sure we have some way to troubleshoot this so we don't get errors. What if our array only had one value in it, one integer, one element? Well, then that's going to be a really crappy array, and we don't want to go any further. So first off the bat, we can say if the length of the array that we're going to be passing is less than 2, well, what do we want it to do? If it's less than 2, hell, just return, let's do a print function and say too small, so we know. So that's how we can take care of that if the length of the array is going to be too tiny to begin with. Now, something I want to do, because I already know how I'm going to code this, we want to have a way, almost like counters, we want to have a way of counting exactly, keeping track of what we see in terms of our array pairs and also outputs of our different array pairs. So we're just going to create 2 different empty variables that are going to sit in memory, and they're going to get filled as we go through, in this case, a for loop. So we want to go through, we want to use a for loop to go through each of the elements within our array and somehow compare it to our target to see if it's going to be a match. So for each
target and number, we're going to get an output, and that output might be that number target might be a very good match for our number of for our specific value in this case, which is k. So with that being said, let's just run through it. It'll make more sense to as we go through it and then as we debug it, of course. So for the number in the array that we're going to be going through, what do we want to do for each number in the array? Well, I want to compare it to another variable I'm going to create called target. Target's going to equal k minus the number that we're going to be going through in the for loop. So for number in array, target equals k minus number. So what does this mean? If we go through the beginning of the array, it's going to first go through the number 1, and k is always going to be 4 in this example. So 4 minus the num, 4 minus 1 is going to be 3. So in this case, when the target variable is created in memory, it's going to fit that with the number 3 when it does that in memory. So what do we want to do with that if that's going to be the case? Well, if the target is not seen, I want to somehow take that target that I get. In this case, it's going to be 4 minus 1 is going to be 3. If that target is not seen, what do I want to do? So if the target that we're computing is not in scene, and scene is the variable that we have created above, we're going to want to take that scene and add the number to it. So again, the number is going to be this portion here. We want to add the number that we just computed that target with. And this will make sense because again, we're doing it in pairs. So this is 4 minus 1, and we're going to get a target of 3. So we care about the 3 and we care about the 1. Because we already know now that that's going to be a pair that's going to equal up to our ultimate value of k. So now as we're starting to adjudicate this list, we're saying, all right, if the target's not in the scene, add it to scene. What else, and what do we do in Python? We want to put an else statement in to say, if it is in scene, what do I want it to do? Well, if I know that if the number that we're utilizing to create the target is already in scene, well then I know I have a combination now of target and scene. Target and number that are going to combine together as a pair to make the value of k. What the hell does that mean? Meaning, in this example, we'll do 4 and 1 again. So 4 minus 1 equals 3. So now going through this next line here, if 3 is not in scene, well, scene is empty at this point, add the number 1. So then we should get the number 1 to pop up here. But then what's going to happen is the next time I go through this piece here, it's going to say, the next loop, it's going to say for num in array. Well, it's going to be then 4 and then 3. 3 is going to be the next number in the array. Target equals 4 minus 3. Target's now going to equal 1. If target not in scene, well, we just know in the last for loop we have a number 1 in here. So it is seen. So what do I want it to do? Well, so now I have a combination of 1 and 3. I'm sorry, this is going to be 3 at that point. So I'm going to have a 1 in scene, and I'm going to have a 3 in num. So what do I want to create that pair, that 1-3 pair that's going to equal 4. So what are we going to do within our else loop? We want to now start to adjudicate our output. And this is how we're going to do. So we're going to take our output, our empty variable output, and we want to add to it. What do we want to add? We want to add the minimum of what? Well, of number or the target. So in this case, so the first one was 4 minus 1, and it was going to be 3. And then the next time we had 4 minus 3 is going to be 1. So we want the minimum of that number target combination. So the minimum, the second time it runs through, and this will make more sense if we go through the minimum when we do this, it's going to be, this will be 3, and this will be 1. So the minimum between 3 and 1 is 1. So it should print a 1 first. And then I'm going to then, whoops, a daisy. Then we want to do the maximum of the same thing, of that same combination. Get rid of that out of the way. So now what I want it to do is say, again, between 1 and 3, now give me the maximum of that number. Let's see if our parentheses match up. Yes, yes, and we're in the add method. Wonderful. So again, as we go through this in the debugger, it'll be a lot cleaner for you. And then as we're going through this, I want to do one more piece in this for loop, which is then we want to give an output, right? So I'm just going to put, just for the sake of cleanliness, have a new line, and to that we're going to join. I want to join something. This will make sense to you again as we go through the debugger. I want to map, and through that map I want to create a string, and I want that list to be from the output that we created, which again is going to be this. Right now it's just an empty set, but I want it to print out that output, and that's what we're adjudicating here in this else statement. So as I go through, just want to check my parentheses. Good, 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 sweet. All right, so Now, in order to make any of this even do anything, after we printed out a tuple answer, we're going to see if we have the right answer. We're going to first have to call this function into place first off. So, how do we do that? Well, I'm just going to pass through, call our function, pass through the function here, pair sum. So we're calling the function we created. I need to first put an array, and we said we were doing, what did we say we were doing? 1, 3, 2, and 2. That's our array, and then I have to also give it a k value. In this case, we're doing 4. So let us pop it in and run the debug. We're doing pair sum, so that's what we're going to run here. And I can do console, but we don't even need this right now, but it's going to keep popping up, I believe. So, start off in the beginning. Let's F8 through there. So first off, again, remember for functions, whenever you're running through a function in the debugger or even in Python code, it's not going to run the function until you call it. So that's why it jumps from line 13 where I started all the way down to line 31, because now it's calling the function pair sum, and it's checking, do you have 2 arguments? Otherwise, we'd get an argument error. It'd say, you're trying to pass 2 and wants 3, or vice versa. So pair sum, we're giving it 2 arguments. We can see in our function it wants 2 arguments, so we're going to get to the next line. So in memory, we have an array, which is a list, and it's 1, 3, 2, 2, and then we have our k, which is equaling 4. So now we are good. We can start to run through the code. So if the length of the array is less than 2, it's not. Our array has 4 elements in it. If the index is 0 to 3, so that's going to be a false. So since it's false, it's not going to finish that loop. It's going to jump out of that loop and go to the next line of executable code, which in this case now we're at scene. So scene is going to be a variable. It's an empty variable, just going to create set. So in memory, we're going to see the variable scene created, and it's going to have an empty set. Same thing for output, nothing special there. So we can see in memory what we're creating now on the computer. Now, first for loop, for the number in the array. So for the first number in the array, it's number 1. So it's going to give me num equals 1. Target equals k minus num. So that means target is another variable we created, and it's going to equal 4 minus 1, which is going to give me 3. So now it's going to say target's going to equal 3. Now this is where I want you to pay attention. So if the target is not in scene, so we can look at scene. Right now, scene is an empty set up top here. If the target is not in scene, well, target is 3. It's not in scene. I want you to add the number. And the number right now in memory is 1. So since 3 is not up in here, add the number. So we're going to F8 through there. And sure enough, in scene, now we have a 1. And now we can go to the next number in the array because we're still within this loop here. So for number in array, so now the number is 3 in the next number in the array, which is correct. Now we're going to have target equals k minus num, or 4 minus 3. So now our target is going to change within memory, and sure enough it did. Now watch what happens here. If target not in scene, target is 1. Is target not in scene? That would be false. It is in scene. So we're not going to add it. We don't want to add it 1, 1 again. It's not going to make any sense. We already have 1 within the scene. So that means this is going to be false, and it's going to jump to the next executable line of code. So it had better go down to line 27. And sure enough, it does, because now we're in our else statement, because that if statement was false. So it's got to go to the next executable line of code. We have to keep going until we hit it true. So now this is going to be, this else statement is simply adjudicating the output set that we have up here, an empty set. So we're saying in output, I want you to add. I want you to add the minimum of the number or the target. Or right now, the number is 3 and the target is 1. So the lowest of that, the minimum, is going to be 1. So the first element here in this tuple is going to be 1. And then for the second element, I want you to give me the maximum. That is of the number or the target. Number is 3, target's 1. Maximum is 3. So now this tuple had better print out a 1 and a 3 if we coded properly. So I'm going to F8 through there. So now in our output, sure enough, we have a 1 and a 3. Good. So within this dictionary now, we have a 1, 3 tuple. Sweet. I like it. Now we still have more numbers in the array to go through. So now we're going to F8 through there, and the number is going to change to 2. So now we're going to have 4 minus 2. It's going to equal 2. Now, if target not in scene, target is 2, it is not in scene. So it had better go to the next line 24 and add it. And sure enough, it does. Wonderful. So now we have 1, 2 within the scene. The next number that's in our array is the number 2 again. So it's going to stay 2. Like all good math, target's going to stay 2. If target not in scene, well, target is 2 right now, and it is in the scene. So this is going to be false. So we have better jump to our else statement. And sure enough, we do. Same thing now. Output. Right now, output has a 1, 3 tuple, and we want to add to it the minimum of the number target. Well, the minimum of our number target in memory right now is a 2. And the maximum of our number target in memory right now is also 2. So we had better get a 2, 2 show up in memory. And sure enough, we get a 2, 2. And we can kind of see our code is working because 1, 3 is 4, and 2, 2 is 4. So this, it should be, right? I mean, it makes sense. We're doing the math right here in this for loop. So now we run through all the numbers in our array. So when I F8 through this for loop here, it's going to leave. And sure enough, it did. It left the for loop. Why? Because there were no more numbers in the array. We were done. Next executable line of code outside the for loop is this print statement. And that's where we have print is equaling, we want a new line, and we want to join. And by that joining, we're going to create a string of our list of outputs. So right now we have 2 outputs, and that new line is just going to mean that's going to take 1, 3, and on a new line it will put 2, 2. Again, if I did this properly. So I'm going to F8 through there. Everything's out of memory, and I just want to see if it actually did it right. Hey, there we go. Awesome. So I'm in the console now. So this was the... Let me bring this up, and let me go down here so we can see it. So this is the printing out at the end in here in the console. We printed out, I wanted a new line, and I wanted to join, and then map creating a string of the list. So we have a tuple of 1, 3, and a tuple of 2, 2, and it got those from the output. From the output variable that we created. Right now it's empty, memory's done because the code is done, but you saw the output was growing. Every time we got through this else statement within the code, that output was growing. So this is a good opportunity. You can look up join method. You can look up the map method if you need to. Play with this. Change your pair sums. Get to add another number and see what happens as you run through your code. Try to break it and then debug through it and see where it's going wrong and maybe what other tests you might need to put into the code to make it executable. I highly recommend memorizing this aspect of code, again, as another aspect of the array job interview questions for algorithms, for array algorithms. Not array specific, but we're using it for this example. This one is primarily just called the largest sum, where we're going to take an array that has positive and negative integers and find the maximum sum of that array. So first off, we're simply just going to create, we'll call it largest. Nothing too crazy there. We're going to pass an array through it. So first off, we want to make sure that the array is even an appropriate length in order to create a sum. So we're just going to have if the length of our array equals 0, well, what do we want it to do? We can return too small. Nothing fancy there. So just putting in a check into the code early on that if the array is going to be, if the actual element count is going to be equal to 0, there's no point running this code and we don't want to crash it, so we're going to tell it to print none. So first off, we're going to set the first element that is within the first index position within our array. We're going to set it to something that we'll name it a variable of max sum, and that's going to equal, we want another variable, and this is going to equal the first element within our array. Now we're creating 2 different variables, maximum sum and current sum are both equal in the the array, the first element of the index position 0. The reason that you're going to see in a second why we want 2 different max sums and current sums as we do the calculations. So we're just going to create a simple for loop, for num in array. And what we want to do is we want to make sure we can go from, we already accounted for the first index position of array 0 in line number 10. So now we want to go from the next index position, which is index position of 1, the second number in the array, and go all the way to the end. So that's just going to be starting at 1, and then the colon for going to the end. Then we can close it off. So in our for loop, we want to count for each number, but again, we don't have to account for the first index position because we already did here in this line. So now we can start from the second index position and go to the end of the array in this counting, is essentially what we're doing. Now what we're going to do is we're going to compare the current sum, which as you can see is set to the first element in the array of index position 0. We want to compare the current sum to the maximum of a new sum compared to the number that we have. So what does that mean? So we're going to redefine current sum here. We're going to say current sum is going to equal the maximum. Well, the maximum of what? Well, either the current sum, whoops-a-daisy, plus that number that we're going to be calculating. So this is going to, do I have what I want to put? Oh yes, but or the number. So if we want to calculate the maximum sum, we're reassigning what current sum is going to mean. Let me get this out of the way here just for a second. So this is like a current sum tracker, if you will, this particular line. So what we're saying here is we want to redefine the current sum to equal whatever's the maximum. Is the current sum the maximum? plus the number. So if it was, I don't know, let's say 2, and then now the number is 3. So is it the maximum 5, or is it the number 5? I'm sorry, 3. That's going to be the maximum. Whichever is the maximum, we want to add that to current sum. Oh, that was stupid. And then we also want to create, compare the maximum sum to that current sum. So we're going to have we have a current sum tracker, so now we'll have a max sum tracker. So that's just simply going to equal the maximum of the current. And we're gonna of course debug all through this. Our current sum, or the max sum. So let me get out of there. I don't want those greens in place. So we're tracking the current sum, which is simply whatever number that we're iterating through in this for loop. We're adding it to the previous current sum, and then or the number. We're going to compare the maximum, which is going to be greater, that number or the current sum plus the number. And then we're also going to be tracking the maximum sum, which is the maximum of the current sum, which we just computed a new current sum, or the max sum, which we already have starting at our first index position of 0. So this is just creating a, like we said, a running sum, essentially, a maximum sum, largest continuous sum of the numbers, largest continuous sum. So of course, when this is all said and done, we need to return something, right? So let's come out of that for loop, and let's just return max sum. That's what we're after. So now in order to even call this and run it so we can debug it, we're going to call our defined function we called largest. And in that largest, we're going to call the function. There we are. Now we're going to put our brackets to create a list. So we're going to put, I want to start with not a 1. So when we debug it, it makes sense in terms of the coding. 10, negative 56, I don't want to go too crazy. Negative 12, 3, 21, negative 19. All right, so we have our array that we're going to pass through. So first off, let me run this. Do I have largest sum even here yet? No. So let me just come across here and let me run largest continuous sum, and we're going to get 38. So at least we don't have any errors yet. Let me get this out of the way so we can see everything in one shot. Whoops, excuse me. Awesome. So now we're going to go debug this, and we're going to see exactly what's happening within the code. So we're going to run our debug. And this is largest continuum sum. All right, so of course, once we're starting our debugger on our defined function, but as a FA through that, it's going to jump right down to the next executable code because we don't execute functions until they're called. So now we're calling it within this print function, we're calling the largest function. So we have our array. So we assume that in memory, which it did, it's going to place that array within memory. So there we have our array as a class list. So first line, if the length of array equals 0, well, that's false. So we know it's not going to return print too small. It's going to jump out of that line. It's going to jump out of that if loop because it's greater than 0, so that's false. So we want to go to lines that are only true. So next, max sum equals current sum equals the argument of 0. So that's going to be true. So that's going to create in memory. It should create the array of it should create max sum equals current sum equals 7 because that's the first element within our array of index position 0. So we're going to fade. So sure enough, we have max sum is 7, current sum is 7. So now we have 2 new variables that exist within computer memory. Now next line, for a number in the array that we created starting at index position 1 going all the way to the end. So index position 1 is already accounted for in that previous line 10. So now we're going to be starting in this example the array starting from number 1 all the way to the end. We're going to go number by number. So first off, it puts in memory a number 1. So we want to say current sum. This was our current sum tracker. So current sum right now is 7. So we want to equal the maximum of 7 plus 1 or 1. Well, clearly that's going to be 7. I'm sorry, 8, excuse me. So you can see up here, current sum now changed to 8. So that was appropriate. Now we're going to work with the max sum tracker. The code's going to take the maximum of either the current sum, which right now is 8, or the maximum sum, which is 7. So it's going to take 8. It's going to redefine max sum to now be 8. So if you see up here, F8, maximum sum turned to 8. So max sum is always going to come after current sum because we're taking the maximum of this continuous value. So now the next index position of 2 is actually the number 2. So we're going to F8 through this. So sure enough, our number 2 changed. Now we're going to do current sum is going to equal maximum. Maximum of what? Well, the maximum of the current sum, which is 8 plus 2 of 10 or 2. So that's going to turn the current sum to 10. And then the max sum is, well, the maximum of what? Well, the current sum or the max sum. Well, the current sum is 10, the max is 8. So it's going to turn it into 10. I'm going to keep doing this. Now we're going to get a negative 1. So current sum is the maximum of the current sum plus the number. So that's going to be 10 plus a negative 1 or negative 1. Well, 10 plus negative 1 is going to be 9. So it's going to create it to 9. So here we have the maximum sum. This is why we did that maximum counter, because now look what happens. So far into this code, we've always seen the current sum being greater than the max sum. Now we're seeing the opposite of that. So now the maximum sum equals whatever's the maximum, the current sum or the max sum. Well, it's currently the maximum sum. We want the largest continuous running sum of the array. So it's not going to change the max sum to 9. It's going to keep it at 10 as we go through the next number, which is now going to be 3. So now we're going to F8 through that. So now the current sum is 12, max is 10. So you know what's going to happen. It's going to turn the max to 12. And we're going to go through this. I like the negative numbers because it really brings it home. Here we go, negative 12. Let's run through current sum calculations. Now current sum is 14 because we did 26 plus negative 12. And that was obviously going to be less than the number of negative 12, even though it was going to be 14. So the current sum became 14, but the maximum is now looking at, well, what's greater, the max sum or the current sum? And clearly it's the maximum sum. So it's going to take 26, and it's going to completely ignore that 14, and it's going to go to the next line of code, which is going to be 3. So now 26 is going to eventually come up into, oh no, see that? Yep. So it's still 26 because current sum is only 17. We wanted the largest continuous running sum. So now the current sum is now finally greater than the max sum. So now the maximum sum is going to update. So there we go. Now we have maximum of 38. So I'm just going to finish running through this. Negative 19 should be the last one. Return the max sum, and it sure did. We'd have another console of 38. So this is not just a simple addition. We wanted to go through and find the maximum, the largest running continuous sum that we could find within the array. So nothing too fancy, nothing necessarily new here in the code. The only thing we've done a little differently than previous is we've started off with both variables being tied to the same input and then being adjudicated later differently, depending on the running sums and the sum trackers we were using, either current sum or the maximum sum. Just start to put these into memory so you have your interview algorithms at call whenever you need them. And the largest benefit of all of this is that when you are working on different projects, you can always say, well, I need to do X, and I can pull that from this array, or I can pull this from this array. How the hell do I go from beginning to end? How do I go reverse? Oh, I can take this from this array that I've memorized. So that's the importance of memorizing fundamental pieces early on. So then you always have them at your disposal. Yeah, the array is going to be given a string of words. We want to reverse all the words. And we want to do this. First, we can show just using Python built-in methods, how we can utilize that, but then also how you can code it by hand from scratch without using built-in functions. So if you were doing this in a different language, you could pretty much do the same thing. So if we're starting with a string, this is the best. How can we finish with the string? Best is this. And you'll notice we also did preserve the spaces in between the words. And we can also insert something else instead of the spaces should we want to, utilizing the join method. So first off, let's just start to we'll call it reverse, and we're going to pass a string. We'll just call it S for this purpose. So we're going to pass a string as the argument through our function that we're creating. And what if I could just simply say, and I'll explain what all this means. I'm going to return, and I'm going to put a dash in here just so you can see what that's going to make, what it's going to make the code do, so then you can understand. Reversed, and we're going to have to split our particular string that we have. So let me explain to you exactly what I have in here. We're going to and remember, it's just like in mathematics with PEMDAS, parentheses always take priority, and we work from the inside out. So starting with our first set of parentheses, and they're highlighted here in green. So s.split. So what is that actually doing? So s is our argument that we're putting through our function reverse that we defined, and we're splitting it. We're applying this split method on it. So what does that do? I wanted to quickly show exactly. Let me bring up, I think, all right, I'll bring this one up for now. So let me copy what we have here, and I just want to show you something. So what if we did, and I'm going to show you like a backhanded way in a sense of doing this if I wanted to. If I wanted just to make it as simplified as possible. So what I'm essentially doing when we do this, so make sure my tabbing is appropriate, I'm saying take the argument s that we put, and I want you to create that new variable be a split. So what does that do? So all we're doing is we're taking our argument here, and we're applying the split method. I mean, it's going to split that string up. So what if we passed, we'll pass this, copy. We're essentially going to be calling our method that we have there reverse. And I'm putting in that string that I just copied from before. This is the best. So right now my return is, it's calling for the s.split. So we've covered that. So we could take this part out, right? And then we have the reversed function here that's being utilized. Now there is also a reverse in Python. There's a reverse and there's a reversed, and one's going to be on a string and one's going to be on an object. So all I'm going to do, again, to keep with this method of simplicity, I'm going to get rid of all this for just a hot second. So we've taken our argument s, which is a string, and we're saying take that string and now here and split it into pieces. And then with those pieces, we have a new s now, which is a split version of that string, meaning it just segments. So we have the string, this is the best, so it's going to take this, and it's going to take this, and it's going to take the, and it's going to take best, and it's going to separate them. It's going to split them up. And then I just want you to reverse it. I'm going to put the reverse method, the dot reverse method, on that string. And then I want you to return to me, well, s, right? That's what we're doing. So I'm calling now in this print function here, I'm calling the reverse. And let's run it and then make sure we can debug it to make sure it makes sense to us. So best the is this. So first off, notice it returns a list. The letters are not reversed, the words are reversed, the elements of each of the words are reversed, and they're separated here by commas because it is a list. So we don't have anything representing the spaces except the space here, there's a space here, and there's a space here. So let me go through this. So first off, it's going to create the variable s, and it's going to put this is the best. So it's taking a string that I'm giving, that I'm assigning into this function reverse that we just defined. I'm going to FA through it, s.split. So you can see really quick with the s.split, what it did was it took that string that we had, this is the best, and it broke it up into, and now it's a list. See, class list, this is the best. So it just broke it up into 4 different elements, 0, 1, 2, 3 inside of our list. And now we're going to take that new string s, or that variable s, and we want to apply the reverse method to it. So FA through that, and now you can see up here, best the is this. And then we're just returning what s is now. That's it. So that's exactly what we saw boop, 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 down here in the console. So we know we're working. So this is kind of doing all of that with one modification. This is doing all of that. That one line of code that I'm going to show you next is doing all of this plus one more thing. So we have we're splitting it, we're reversing it. Now you notice this is not reversed, this is reversed, because that's going to be on an object. And then we have the dot join method. So the dot join method, and then there's two parts, excuse me, to the dot join method. So this, whatever we have in between the quotations here, we're telling Python to join the sequence that we're creating, in this case via a hyphen. We can make it whatever we want. I'll show you how we could do that in 2 different ways in a second. Calling the join method is just going to return a sequence that's joined by the separator. So we're telling Python, here's the separator that I want to use, and what I want you to do with that separator, I want you to join what you reversed after you split it into a list. All right? So with that said, let's be consistent. Let's take this. I'm going to bring you over here. So, of course, this is under sentence reversal, so I'm going to run it. Let's see what we got. Best that is this. So we reversed it appropriately. We no longer have spaces. Now we have our separator is the hyphen. So to show you, let me make it a $sign. We'll run it again. So now best $the is $this. So all I did was with the dot join method, we're giving the separator how we want it to be separated, and then we want it to join it. And if you want spaces, then put it in your separator. And now you'll have spaces surrounding the $sign in the dot join method after we reversed it, after we split it up into a new list. So this is one quick way you could reverse a string utilizing Python built-ins. Another simple way I can think to do it, I'm gonna keep this piece. Another way, a simple way you could have done it is simply just almost doing well, not almost doing, actually doing, indexing through it. So if I'm going to go back to return, and I want to keep it, let's do a star this time. Let's do a space on each, and I want to call my join method. And what I want to do in this join method, I'm going to say, we're going to skip the reverse directly, and I still want to split it. All right, so we still want to split. But now, in addition, I'm actually going to call my list, and I'm going to say, start in the beginning, going all the way to the end, and then reverse that row. So let's run it now, send it to reversal. Besta is this. So I have my string. It's split it, or rather, if we go inside out for parentheses, we did split it first, and then we reversed it using indexing from the beginning to the end, then reverse that order, and join it up with the star with the space on each side. So there's two ways we could quickly do it utilizing Python built-ins. Now, for, like I said, we'll get rid of this. We'll keep our reverse the string, and we'll keep our print statement that we're going to use with the actual string element that we're going to do. Let's do another one that would be more appropriate for an interview because it's not utilizing Python built-ins. So first off, what we're going to do, we're going to, we care about the length of our string. All right. So we're just going to first call up our length, and we're going to say that's going to be the length of S. All right. Nothing too crazy there. And what I'm going to do is we're going to have an index tracker. I need something to track this with. And what does that mean? Let me do this first, and then it will make sense to you. And again, yes, we'll debug as we go through this. So this is going to be my index tracker that I have here. So, oh, I didn't mean to do that. And the reason I have that is because what I'm going to say is while I is less than the length. So what are we saying here? I mean, we have the length as a variable created by the length of the string. So we know this string is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 different elements. We have to include the spaces because white space is included in Python when it counts. So we have the length, which is the length of the string, and we're saying while I is less than the length of the string. Probably could have gotten rid of length and wrote the length S here. And we already have I is starting at 0 because that's going to be our index counter. What do I want to do? While the I is less, right now 0 is less than the string, absolutely. What do I want to do with that? Well, we're going to jump right into an if loop as well. And all I'm doing here is I'm saying if string at that position. So right now I'm at 0 position, right? Because I is equal to 0. So I'm saying in the indexed of 0 of my string, which is going to be here, the T in this case, if the index position of string is not in spaces, meaning we don't have any spaces in place, right? Now, right now, Python is going to be saying to me, what the hell does spaces mean? And that's where we're going to come up top here, and we're going to tell Python what we want to call spaces. And spaces is simply going to be, whoops-a-daisy, excuse me, a space. So what I'm doing is I'm putting it as a list because this is all going to be broken down to lists, and we're indexing. I'm using indexing. So if the index is not in spaces, meaning it's not a space, the element is actually a letter, what I want to do if the element is a letter, because if we're not in a space, here's a space. If I'm not in a space, like the first one's not going to be in a space. You're going to see when we do this, when we debug it, in memory, it's going to pull that T out. If index of 0, because starting at 0, not in spaces, well, it's not in spaces, that's going to be true. So what do I want to do if it's true? Well, I want to create some kind of another variable where it's going to maintain that letter. So we're going to call it word start, and we'll just make it equal to I, so that we know where the word is starting for this index. That's all it's doing. This is just letting me know that a word is starting, and it's going to equal I. So word start in this case will then equal 0 when I do this first piece. So I know that 0 is going to have the start of a letter. Now, I still want to stay within this while and if loop, because what I'm going to say next is while, and again, this will make more sense to you while we debug it if you're not getting it yet, while the length end. I like doing some loop within a loop in a sense. While I is less than the length, and we're going to see that, that's pretty clear at this point, and the index at I is not in spaces, what do I want to do? So while I is less than the length and we're at that position, not in spaces, that still would have been true at this position here, right? Well, it's true, and I want to add a 1 to the I until we hit a space. That's what I want to be doing. So we're just going to simply do I equals plus equals 1. I plus equals 1. So that's again equals I plus 1. We just want to increase that I counter until we hit a space, because I haven't hit a space when I first start this index of the string that we're passing through the definition. And well, then what I want to do, if I am actually doing that, I want to add that letter to another variable that I don't yet have. So what I'm going to do is I'm going to come up to the top again, and we're going to create a new variable. Just we'll call it words. That's what we're doing, right? We'll make an empty list. So now what I can do is we can say within this while loop, outside of the while loop, once we get past that piece of the code, because this is going to be independent of that, I want to append. I want to take my words empty list and I want to append it. What do I want to append it with? Well, clearly from my string, I want to take word start, and that's what we have up here. That's going to be our I at that moment. So we're just recording that variable. Word start from the beginning to I. And I is going to be adjudicated right up above here. So these two pieces of code here, this line 20 and line 23, are going to run, both of them will execute with the same I. And then what I just want you to see, and again, this will make more sense when we debug it, we're adding the word that we collected, or the letter that we collected in that while loop, into a space. So if we collected a letter in here, so I'll let not in spaces, so this would have been, so far as we run through this, so far we have the letter T. So if index of 0 of the S is not in space, that's true, it's T. Word start equals I. Word start is down below here, so equals I. So that's equaling 0 at that moment, which is actually going to be the S of word start. We're calling the index here of 0 to the I, which is going to be that at that point 1, and that's going to give me the letter T. So I'm taking the letter T and I'm going to append that into words, and that's going to be up in here. So what else do we need to do? Well, a number of things. One, we have to then add that, and that's what we're going to do right now. Let me go to the if loop here. So why am I doing that? Because if I'm going to get a space, while I is less than length, if SI is not in spaces, if this becomes a false, meaning I have a space, bam, I want to come down and I want to increase my I so I can go to the next element that's within my string, ergo the argument that I'm passing through the function that we are defining. And when all is said and done, what do we need to do? We need to return something. So and I want this lined up with my while, so I'm going to return. Well, what are we returning? I'm going to put a space there because I just want to put a space in between my join method that we're going to be using, so it's a little cleaner. And we're reversed because we collected our word list. Our words variable here is going to contain the breakdown of this is the best. This is a lot of work just to break this down so that it's in a complete same thing. This is the best, and you're going to see that. And then at the end here, we're going to call the reversed on an object. And we have our object as S. That's what I called it, correct? Yes, S. So that's all we did there. So nothing crazy. So let us debug. Well, first off, let me run it. So this is sentence reversal. So now we have this is the best. And if I didn't want those spaces in the letters, we can do that. But you'll notice here, not only did we reverse the letters, the words, we reversed the letters as well. So let's debug and go through this and see what's what. I want to see if I can open it up so we can get everything. It's going to be enough. Let's go like that so we can see the whole shebang. All right, run. I want to debug this, and this is sentence reversal. All right. We're going to see everything on the screen. All right, let's go FA through it. So like all code, it's not going to do the function. It's going to go down to our print statement, which we're calling the function we define and putting in the string, this is the best. Now, first thing, the length of S, it's going to give me a 16. And again, if you count the letters, you have to also count the spaces. And then we have spaces. This is an empty list, nothing special to it. With a space in between words is also going to be an empty list. And then we have I equals 0, so it's going to create I equals 0. So while I is less than the length, we can see is 16 up top here, and the length, the I right now is 0, so that's true. So we go to the next line within the loop. If si not in spaces, so I is 0, index of 0 is t. It's not in spaces because spaces is an empty space. So that's true. So it's going to go to the next part of the loop. Word start equals I. So now it's going to create a new variable in memory called word start. And it's going to equal I. And at this point, I is 0. Next line, while I or 0 is less than 16 in this case, which is true. And remember, and loop both have to be true. And si, which is 0, which is t, not in spaces, true. So we have true and true. Then it absolutely will execute this next line in here. I equals I plus 1. So now I is going to go from 0, which it started out, now to 1. And then we're going to go to the 2. I messed up my spacing, did I? No. I thought I messed up my spacing there for a hot second. So let me... Boom. I want to start that over for you guys. Run. Oh, no, I don't want to do that. I want to debug. Let's get it in there. Let's get it in place. I want to show you exactly where I went ahead of myself. So let me go to where we got. So while I is less than length and si not in spaces, I equals I plus 1. So we did that. We got the 1. And we can see that we have nothing in place yet. Now, while I equals less than 2, so it's still doing word start still 0. While I is less than length and si is not in spaces, we want to keep adding to the I. So what you're going to notice here is, which you don't see it happening in memory except for the updating of the I. We're going through this first word here because we haven't gotten to spaces. Once we get a false here, it's going to stay in this loop here, this while loop. But once we get a false, then we're going to jump down below and we're going to append. So right now in memory, we have an index of 0 and 1, which is t and h. So we're going to F8 through there. Now we have an index of 3 here. So 0, 1, 2, 3. So S, F8. Now we're at index of 4. Index of 4 is a space. 0, 1, 2, 3, 4. So now I is a space. So while I is less than length, well, that's true. 4 is less than 16. And the index of that position, 4, not in spaces, well, not in spaces is space, that's a false. So it should jump me out of this loop and pop me into words down below. There we go. So now what's going to happen, we're in words.append. Words was an empty list. You can see it here in memory, an empty list. Words.append. We're appending from our string S, word start. Word start is 0 to our I. All right. What is my I right now? 4. So it's going to take index of 0, t, to 4. 1, 0, 1, 2, 3, 4. So when I F8 through this, it should pop the word this, there it goes, this, into the words empty list. Because we hit a space, so that jumped out that first word. So I equals, now we still want to increase our I one more to get out of that space, because otherwise it's going to be stuck in number 4. So now I equals 5. So now what's in 5? It's the letter I. So I'm going to go through. Word start is now going to be 5, because it's going to equal I. That's fine. 5 is less than 16. 5 is less than 16. That's what we have here, while 5 is less than 16. And the index position S, 5, is not in spaces. Well, we know index position 5 in the S is I. So that's true. So it's going to F8. So we're going to go to 6 for the I. And that should be the same true here for S. 6 is good. Now 7 is a space. So it should jump me out of this while loop again and go down and append the word is to my word list, the empty list that I had here. Same thing now. Now it's just going to be for the, we increase our I to 8 so that we can get to the T in the word the. So 8 is T, 9 is H, 10 is E, 11 is a space, word append, this is the. You can see now in the words variable, now we have the. And again, we're going to go F8 again. Same thing. While I is less than length, I is 12, absolutely is. Not in spaces. Nope. Word start's going to be on 12, which is excellent. That's going to be the B in the word best. So we're going to be going 13, 14, 15. So we get to 16. So now there's no space after this, so it's not going to jump me out of the loop because of the spaces. While I is less than length, look what happens now when I get, before I execute this code. We haven't executed yet. We're just sitting on it. I is 16, length is 16. This now loop becomes false. This while loop now becomes a false. So we're going to skip this and we're going to go down to words append. So now when I execute this words append, now we'll get the word best up in our variable top here. And there we go. We got best. I equals I plus 1. It'll execute it. Now it's 17. While I is less than length 17 is greater than 16, this whole loop now becomes a false. I'm not going to get past this first line. So I got to jump down into my return. And what am I saying here? Return with no spaces. Join these, because you'll see we have spaces already in our words list. Join, no space. Join this reversed S, the string. We'll print it out, and I can go to my console. Where did my console go? That was rude. And we're printing out letter for letter of exactly how we did that. And you'll notice the difference, we got the letters this time and not the words from before, is we're reversing the entire string. And if you recall in memory, that the string was not, it wasn't split into its constituents. Whereas in the code we did before, we were calling the split function to break up those pieces. If we utilized the split function in this, we would have gotten the same outcome in regards to the words going backwards. So just really quick, another way I want to show, without even having to use the join method. If I did reverse, this, let me just quickly say, this is the one that I would memorize. I mean, the other ones, you got the functions, you got the built-in functions in Python, and that's cool. But this is the one that I would pretty much memorize and work with. Not only is it utilized in other languages, as long as you have loops, of course, but it makes the most sense in terms of going element by element, taking that string as an argument and breaking it down element by element and creating counts, and indexing counts, and then building it, rebuilding that list, and then doing what you want to do with it. And having a number of different loops within loops and different conditional statements. Here we're using the end Boolean end statement to get a true and a true. Otherwise, we're going to jump down to the append. So this is a really good exercise. But I just want to show one more semi-piece. If I simply just had we could return, and if I return S, because that's what, you can't see it now, but let me get rid of this, I'm sorry. That's what we're calling. So if I took my S and I split it just like I showed, and then we simply could just go beginning to back. I gotta go to test now because that's where I am. I want to quickly show that what you could do is not only you sit there and say, we didn't reverse anything. The point I wanted to make with this was inside the print function, since now this is a string that I have, I can call the reverse, instead of not reverse with a D, but just reverse on it. So I can run it, and then I'm going to get my split on the list, grant M, I, hello. So it's actually going to take my string, it's going to reverse it, or it's going to reverse the string that it returns after it goes to this reverse function that we have. I should probably call this something else so it's not confusing. Let's just call it rev. So I'm calling my function that we have, hello, I am grant. So the function is going to take that string, hello, I am grant. It's going to split it. So we're going to have one list with each of the elements in its own for it. And then we just did beginning to end -1. So I think I showed you guys that one earlier on. I really like this one personally because I like the idea of the indexing, because when we get into data science and machine learning, we really utilize a lot of this indexing when we're messing with databases and so forth. Given two arrays, we're assuming no duplicates within those arrays. Is one array a rotation of another? If it is, we're going to return true or false. So they have to be the same size and the elements, same size and elements, but they're going to start at a different index location. This is going to be a big O of n. It's going to be linear. We're going to go through each array 2 times, but it's O times 2n. And again, the 2 is not going to count because constants are going to be nothing as you get infinitely large. We want to select an index position in list 1, get its value, and then we're going to find the same element in list 2 and see where it is in that index. And then from there, we're going to go index position, because again, they should be in the same size, same elements, and start index at different locations. So if I get to index position 0 of list 1 is the number 2, and number 2 is index position of 4 in list 2, then when I go to index position 5 in list 2 and 1 in list 1, it should be the same next number. So, having fun with that, let's run forward. So we're just going to call it rotation, and just like I said, we're passing 1 list and 2 lists. Those are going to be our arguments for the defined function. And then we're just going to do a quick edge check here. If they're not the same length, then there certainly cannot be a rotation of each other, right? So simply if the length of list 1, we do want to close that off, does not equal the length of list 2. So all we're doing here again is saying if it doesn't equal the list 2, then what do we want to do? If the lengths are different, and even rotation, the lengths have to be exactly the same, the elements have to be the same, just a different index location, well, we just simply want to return false. So we have an edge check in place. Now what we want to do is we want to, in memory, we want to create the first element of list 1. We want to store that into memory. So we're just going to simply say that we're going to call it the key, and that's going to be of 1. And how do we call the position? Just 0, because it's a list. So we can just index to it, index position 0. So we have our first variable. And the second one we're going to call key index. We're going to create a counter, and we're going to initialize it to 0. Now this is going to be what we're going to be counting as we're looking through the second list to see what that number, what that value is in that index position. So now we want to iterate through list 2, trying to find this key, starting at index 0. Because remember, when I pass the list 1, I'm already going to have in memory key the first element of list 1. So now I want to pass through list 2 and say, hey, where in your list, at what index position do you have this value, whatever this value is here? So in order to do that, we're going to do our good old for loop. So we'll say for I, and we're simply going to do the length list 2. So now we can iterate through list 2 trying to find this key. So what we want to do is we have our for loop for I in range. We're doing the range because of course we want to go for the full length of the list. And we're doing index positioning, so we want it to start at 0. Because length of the list would just count the elements. So if list 2, because we're doing 2, right? And we want to say if the index position of 2. So if the index position that I is currently at in index number 2, if it equals the key, well, what I want to do. So if list 2 has the same value that we sorted in the key, well, I want to create an increase in the key index. I want to change the key counter. I wanted to make that index, sorry. So what this is going to mean is that as we go through this, let's say I is at 2. So for 2 in range, because there will be more than 2 numbers. If list I if the element that's at position number 2, and let's say it's 5, equals the key, and let's say the first element in list 1 was 5, so let's say they equal each other, then I want the key index to now be 5. I want the key index, I'm sorry, 2, because I was going to be 2. I want the key index to be 2. So then what that would tell me is that for list 1, this element, the element at this location, the value at this location, equals the value at list 2 index location at index of whatever it was at that point, of index of 2. And yes, we're going to debug this, of course, as we go through. Now, once we have that piece in place, the next thing I'm going to want to do is I'm going to want to break out of this code. Simply because I want to force it to the next line. So once I find the index in list 2 that is equatable to the appropriate index in list 1, I then want to break out of the code. We only need to do this. We don't have to do this once. I mean, this is because we want to jump out of the loop. That's how you force a jump out of the loop. So now we're going to say if our key index equals 0, which we don't want it to, right? This would be true if we didn't find the key in list 2. So that's the only time that this would be true is, again, if we did not find the key in list 2. So we're going to return false
because it means that we can't even do a rotation because it's missing one of the key values. This is missing the same value. So now we're just going to now we want to go through list 1, and we're going to iterate through the list 1, but we want to iterate through list 1, and we want to iterate through list 1 until we find that element of list 2 that matches. So again, this will make more sense as primarily as we debug it, of course. That's the best way to learn anything. So we're just going to do the range of length of list 1. Whoops, went too far. And again, this will make more sense. So if list 1 index 0 equals the value of 1, and we find a 1 in list 2 at index 4, then the key index at that point is going to be 4. This up here is going to be 4. So the value of index position 0 list 1 might be 4, but the 4 in list 2 is not showing up until index position 4. So this will make more sense when we debug everything. So now what I want to do is I want to create another variable, and we're going to name it t. And what I want to do is this is just going to create we'll call it the new index for list 2. So we'll say L2 index. That's what we're going to call this one. And what we're going to take is we're going to take our key index, and we're going to add it to x. And this will be a good exercise for modulos as well. We want to take a modulo length of list 1. And this is going to become the index now for list 2. What we're doing is we're going to reassign the index for list 2. And this is where you're going to see the comparison. So if list 1 position of x, all right, so if the index position of x does not equal list 2, and this is where we're going to change its index, L2 index. So we're getting the value. We're getting the value that we've created here, and we're checking that index. So what we're saying is if the list 1, if the value at that index position does not match the value at this index position, then of course our good old-fashioned we want to rerun, Jesus Christmas. We want to return false, all right? But otherwise, we want to return true if this first line of code here is going to hold right. So why do I have I'm going to call in that loop, right? I wanted to break inside that loop. Okay. What I was looking at just now is why I had a red up here telling me that there was an error. And my break was on the outside of the loop, but I want this break to be inside this loop so that once I actually do satisfy this, I want to break out of that for loop and jump into the next if loop. That's all. So let's actually run this through and let's see if it works, and then we can debug it. So we're going to call our function. My goodness, I can't do these so early in the morning. We're going to call our function that we created, and we're passing 2 lists, so we're going to do brackets. So we'll put this one in order, and I guess we'll go up to 7. We'll do a comma, and we're going to do another list. Now this next list has the same 7 elements, right? But the order has to be the same, but the starting point, the indexing point, will be different. So we'll do it as 7, and then we went to 1, 2, 3. So that's 1, 2, 3, 4, 5, 6, 7. So we have, this is a rotation, so this should return a true. But like I said, we're going to go and debug it, and then we'll go through that. So I'm already in array rotation. I'm going to run it through, and we get a false. And we shouldn't. I just said we should get a true, didn't I? So y is 7 on what's the same order. So let's go through the code. Why am I getting the wrong answer? Then they will return, so it's going to jump into this. It's going to go here. We'll create those 2 variables for I and range. So this will be starting at 0 plus equals key index 1, key index I, break,
If this is a false, oh, watch this. Let me try it now. True, yep. So I was breaking out of this loop too early. My mistake. So now we get a true, so now we can actually debug this. So I'm gonna hit there. Yep, array rotation. Let's load our piece into memory. All right, actually we'll keep it on the debug for now. I'm just gonna bring this down a little bit. So we have our two pieces in memory. We have our list 1 and our list 2 and their appropriate values. And you guys don't need all of that, so we can just do this. See a little bit more. So if the length of list 1 does not equal length 2, return false. It does equal the same length, so it's going to jump down to the next aspect of code, which is we're going to create a key list 1, index 0 in memory, and that's actually going to give us the values. So if we look at list 1, the first index position value is 1. That's why it's a 1. Key index equals 0. That's just the variable key index, and we're equaling 0. Now for I in range, this is the length of list 2. So it's going to iterate through list 2. So the first, the I is going to be 0, because that's where we're starting. If list 2I, so if the index position I, so if I look at list 2, the first indexed value is going to be number 4 in index position 0. If it equals the key, right now the key equals 1, then we'll jump down and we'll break and we'll go down. Otherwise, the key index is going to equal I. So let's watch this go through. So if list 2I equals key, it did not equal key because 4 does not equal 1. Right now the key is 1, and the first element, this index position in list 2 was a 4. So we're going to go check it again. Now it's going to change up to index position 1. Well, list 2 index position 1 is a 5, and we're looking for a 1. So we're going to F8 is going to go through it again. And now it's going to change to I equals 2. Key in still 1 because that's what we created. And index position 2 is a 6. So it's not going to be satisfied. It's going to be false. Now it's 3. Index position 3 is a 7. It's still not a 1. So we're going to F8 through that. Now it's a 4. 0, 1, 2, 3, 4. And now at index position 4 of list 2, the number 1 equals the key index of 1 in list 1. So now that they match, it should take us out of this loop. It should go to key index equals I. So it should change the key index now to 4. Good, which it did appropriately up to up here. Now the key index is 4. Now we can break out of this loop because we're done finding the matching sequence. If key index equals 0, so key index, it started at 0, but we've changed it. This is what it is in memory. Now it's 4. This is almost like another kind of another edge check, if you will. And we're simply it's going to skip over that because that's going to be false because it's not. The key index is now 4. Now what we're going to do is this is where we're going to go over at list 1, changing the index of list 2, constantly upping it by 1 to see where it is that we're going to be within that list. And when I'm done with this, I'm going to do a little lesson on modulo because it may not make sense to some people. So for x in range length of list, so x is going to be 0 because we're starting at position 0 for the range. L2 index equals 4. So how did we get that? Well, the key index right now is 4 plus x. X is 0. 4 plus 0 is 4. 4 modulo, the length of list 1 is 7. So we can go 1, 2, 3, 4, 5, 6, 7. So 4 modulo 7 is 4. If you don't understand that, I'll do a quick video showing how that comes about in just a moment. If list 1x does not equal the list of L2 index, and right now it does not, the index position of 0 is 1, and the list 2 index position of 4, 0, 1, 2, 3, 4, is 1 and 1, so it does. So if they don't match, return false, but they do match. So now it's going to go to the next one. X is going to be 1. L index is going to have to go up to 5. So now it's checking the values at index position 1, which is 2, and list 2 index position, which is now this a 5, which is a 2. So you see how it's going element for element now. So I'm just going to go through that. That matches, so it's going to go to 2 and 6. So now we're at 3 and 3, and they actually do equal each other. So this is going to be false, so it's going to jump back into the loop. Now we're at 3 and 6. So we're at 4, 0, 1, 2, 3. So now we're at 4 for x and position of 6. So 0, 1, 2, 3, 4, 5, 6. And we're going to be matching up we didn't even do it yet. It's not 4 and 6. It's got to be 3 and 7. Yeah, I didn't go through it yet. So it goes to an index of 0 because again, 0 to 6 is 1 to 7, but we're doing a range.
So now we're matching up index position 3 of list 1 and index position 0 of list 2. So 0, 1, 2, 3. So that's 4 and 4. So it did jump into the list. So it's going to do this until we extinguish the range of the list. And that should be it for the range, because we only get up to 6. So once we jump out of the range, then we're going to return true, because we found that these two lists, they have the same length, they are composed of the same elements, and the elements are in the same order, the only difference being the starting index position. So, and of course, if we FA through that, then in the console, it's just going to show us the true that we have. So if people didn't get this, the modulo 4, if you're sitting there saying, how the heck can 4 modulo 7 equal 4? It doesn't make sense. Some people may have even thought it might have been 3 or whatnot. Let me quickly just show why that is what it is. So I'm just going to quickly open up this program here. Let me throw on the tablet. Let me move this. So it's most people. We can actually even make this closer to 3. That's excellent. Do a nice bright green for this. So if I did 12 modulo 5, most people are going to tell me, well, I know 5 can go into the 12. It's the way you're supposed to be doing this is 5 times 0, 5 times 1, 5 times 2, 5 times 3, and we're going to get 0, 5, 10, 15. And you see that it fits in here. So it's going to be, we have a 2 in that spot. So then how do we get to this level of here, 10? Well, it's 12 minus 10. It's going to equal 2. So that's why it's equaling 2. So with that being said, what we had 4 and 7. This is where it gets different, because 4 and 7, we're used to the bigger number being first. But now with 4 modulo 7, what we're saying is 4 goes into 7 4 0 times. So 4 times 0 is 0. So how many times does 4 go into 7? Well, 7 times 0 is 0. 7 times 1 equals 7. So we can't use, we have to use the 0, is my point, because 7 is already larger than 4. So if we're taking that 0, 4 minus 0 equals 4. So that's why 4 modulo that is 4 modulo 7 is going to be 4. If we go to 5, let me do this. Yeah, I'll keep it. If we went to 5 modulo 7 and say, what does that equal to? Well, again, we're at 7 times 0 is 0. 7 times 1 is 7. So we're still in this middle point here. So we have to select 0. 5 minus 0 is 5. So 5 modulo 7 is going to be 5. When we get to 6, it'll be the same thing. When you get to 7, and this will make more sense to you now. Oh my goodness. So 7 modulo 7, everyone knows is going to be 0. We have no remainder left over. But why? Well, 7 times 0 is 0. 7 times 1 is 7. So we can select this. And then we're doing 7 minus 7 equals 0. And that's how we're getting that number. So modulos are always easy whenever we're, whenever it's, it's somebody who's going to be doing the remainder, when the top number, when your numerator is larger than your denominator. It's fairly simple to do. But it becomes, people get confused when the numerator becomes smaller than the denominator. So you have to actually understand how you're doing the math. And that's exactly why in our example, let me see if I can just do this. That's why in our example, oh, that was pretty cool. 4 modulo 7, and because this was at that point 4 plus 0, and so this was our key index value plus the x at that moment, and it was modulo the length of list 1, and this was 7 because we had 7 elements within the list 1. So 4 modulo 7 again was going to, that's why it was going to equal 4, because we were going to end up getting 4 minus 0. So I just wanted to quickly explain that, because I could see people coming up with questions saying, how the heck did you get that? We want to return the common elements as an array between two sorted arrays of integers. Ascending or descending is not going to matter. The example, the common elements. Let me just quickly do this. Let's do on soft wraps. Ascending in the order, integer ascending order. Example, the common elements between 1, 3, 4, 6, 7, 9, and 1, 2, 4, 5, 7, 5, 9, and 10 are 1, 4, and 9. So we want to just take two different arrays and tell me which two elements are the same between them. So let's first off name it up. And what are we going to take through this? We're going to take, like I said, two different arrays. So we'll just name them A and B for this argument. So now we want to create pointers that are going to point to each index and compare the values. So we want to have a pointer that's going to, look at this, index 0 and index 0, index 1, index 1. And we want to find the common elements that are going to exist between. So we're going to use pointers first off to then append into a list. So I'm just going to create pointer 1. And what do we think we're going to do? We're going to set that counter to 0. All right. So this is pointing at index 0 for it's going to be for A essentially. And that's how we're going to tie it together. And pointer 2, what do you think it's going to be at? You're darn right. Same for B. Nothing special there. So we're creating two different pointers, and we're going to tie those to A and B later to dictate a index position. And like I said, I do want to have an empty list because we're going to be appending this. Let's just keep it proper context. So we're going to do a while loop. We want to go through the length of the list essentially and check the corresponding index position. To know if the index value is the same, then we want to add the element to the result. If it's not the same, that's how we're going to get the end product. So while p1, which is one of the variables that we created, while p1 is less than the length of A, because that's what we're comparing it to, and I love using end loops, p2 is less than, what do you think? The length of B. So while and it's that both of these conditions, the point I want to make is both of these conditions have to be true in order to get to the next line of code. So if, while we're going through that loop, if A, so what does this say? So while we're going through the loop, if the index location of A is what? Equal to the index location of B. So if the value at that index location is the same, if the index value is the same, then we want to add the element to the result. So how do we add an element to the result? Well, the result up here is the variable that we created, which is an empty list. So we're just going to good old-fashioned result dot append. And what are we appending? We want to append the value at that point, whatever p1 is going to equal for that index location of A. Since they're equal, it does not matter which one you're going to add from. This could have been B, P2. It doesn't matter. The point is, because they're the same. If you're appending your empty list result, we're only doing so when these two are equal. So whether you did AP1 or BP2, it's the same value. That's all that's going to mean. And now what do we do whenever we we want to move to the next index location? We're going to have to simply change our count, right? So now we can actually move through the iteration appropriately. Now we have to cover for other, oops, look at that, I forgot a colon. We have to now account for other instances. So what if P1, because we have if they're equal to each other, what if it's greater than, what if it's greater? What if the value is, if the index at A element is larger than the one that's at the B element, we want to move our pointer in B only. So how are we going to move our pointer? Nothing crazy. We're just going to say P2, because again, that was our pointer. We want to move it up by 1. We're only moving the pointer in point B since the A element is larger. All right. That's going to cover if that's the case, but we need one more condition, right? We're going to use an else. The only other possibility is that the value at AP1 is smaller than the value at BP2. So all we're going to do in that case is increment P1. We're going to increment our pointer, our P1 pointer, so that it can then still stay within this while loop, because that's what we're doing. And what do we want to return at the end of all of this? We want to return our result that we have here. to see what it's actually going to put within that list. So let's actually run this bad boy and see how we're doing. Common elements, and whoops-a-daisy, get that out of the way so we can see. What are we passing through? We're passing through 2 arrays, right? So let's do 1, 3, 4, 6, 7, 9. Then we have to do a second array because we're taking 2. So we'll do 1, 2, 4, 5, 9, and we'll say 10. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have 6 in each. They don't have to be the same. All right, so let's run this bad boy. Common elements. Yep. So it comes out and it tells me, you can see that, 149. Let's quickly look before we start to debug it, make sure we're good. So let's check if the index positions are correct. We're checking common elements. So they both have a 1. That's true. They both do not have a 3. They both have a 4. They both have a 9, so 149. Excellent. So again, but this was the common elements of A to B. So you'll notice it didn't put a 10, where you would think, why didn't? But it's not a common element. So it is checking the B against the A as well. So let's debug this. Let me hop up here. Let's run our debug. Bring this down just for we have a little more space. So it's going to put into memory our A and B arrays that we have. So this is just our 2 variables, P1 and P2. It's just going to put those in memory. We have them counter at 0. Nothing special there. The results, same thing. Results is a variable. It's an empty list. Now we're going to do our first of all. Pi is less than the length of A. Well, the length of A is, what was it, 6? 1, 2, 3, 4, 5, 6. It is right now P1 and P2 are both 0, so it's definitely less than length A. And P2 is also less than length B, so it's going to run through that while loop. And it says if AP1 equals BP2, result append A with P1. So they did 1 and 1 are the same index position. So P1 was 0, the index position P2, so it was B0, A0. Well, A0 is 1 and B0 is 1, so they add each other. So we're appending our result up here. We're adding that value, which is appending with the value of A to P1. It could have been B, it doesn't make a difference, again, because they're equal to each other. But now we want to move our counter from index position 0 to index position 1, and the same thing for both lists. So our P's are going to change. Now we're going to go through our list again. And do they equal? Well, now we have a 3 and a 2. They do not equal, so it's going to go to our else if. Is the value larger? It is larger, because in A it's 3 and in B it's 2. So what is it going to do? We're going to go down to our else. P, we have to increase our iterator. So now we're running through the loop yet again. Now we're finding it added 4, it appended 4. Trying to see if we can see the list better. Because now at index position 2, we have a 4, and index position 2, we have a 4 in both lists, so they are equal to each other. So we're going to increase the iteration of both. Our pointers, we're going to go through our list again, and we're going to find that it is not, the next position is not true. Now we're at a PI of 3 and a P2 of 4 for our positioning. So 3 and then 4 is because they're not going to equal each other. So we're increasing our counters now to now match each other. Now they're back to 4 and 4 because we went through our else loop. You're going to see that third part of the loop come into play when we get to the number 10. Going through, same thing, 5, 4. Results, they did equal, they both equaled 9. Position 1 was at 5, so that's 0, 1, 2, 3, 4, 5. We had a 9, and that's position 4, 0, 1, 2, 3, 4 in B2. So they did match up. They were equal, so it is going to append it. Now we're at 6 and 6, so that's going to be 9 and 10. So it's going to return the result because we're outside of our while loop. We no longer have our piece. And if I bring our console up, we have 1, 4, and 9. So it took us out of the loop simply because when we got to the past the pistons and 6, we have 0, 1, 2, 3, 4, 5. So when the P1 and P2, the pointers became 6, that's outside of a range. It's outside the array. It's not permissible. So it's going to take us completely out of the loop and then hit the return, the next executable code, which is the return result. All right, this is a pretty simple exercise, guys. Run through it, play with it, see what else you want to do. Change up the numbers. Remember, this is all about finding the common elements, so do it with different sequence of numbers, and do it in different orders, and you'll see different aspects of the code as you debug it. So the question, write a function that's going to take 3 arguments. And in those 3 arguments, one of the arguments can be multiples, but at least 3. First, one of the arguments is going to be bombs. What we have here, we're going to list the bomb locations. This will be very similar to those who know the game Minesweeper. We're going to take rows and columns. So this is what it's going to look like, Minesweeper. Here we have 2 bomb locations. This is going to be a row and a column, Is that. And then we have our matrix, if you will, a 3x4 matrix. So we have our 2 bomb locations and our 3x4 matrix. Now, the bomb at row index 0, first bomb, this one, I just want to give you its location. It's a 0, 0, so row 0, column 0. Bomb at row index 0, column index 1 is the second bomb. That's right here. 3 rows, 3 columns. That's what this translates to. And just so we can, you know me, I'm a visual guy. Let me just bring out the tablet real quick to give you an idea of what it is we're talking about. So we just had 0. Our first bomb was 0, 0, and our second bomb was 0, 1. So if we have this, I'll do that. And this is where our other parameters came in. So we had our bomb locations, right? So there's going to be those 2 arrays. And then we had 3x4. So that's rows, columns. So that means that we are rocking out in terms of this is going to be the columns. So we're 0, 1, 2, 3. And we also correspondingly have our rows, 0, 1, 2. So we can see we're indexing, so we have 1, 2, 3 rows, and we have 4 columns. Now, just like we did with some of our other previous Python exercises, we're creating a matrix, if you will. We're creating like a grid I want you to think of. So the first bomb location, and we're going to identify bombs by -1. When we're doing this code, that's how we're numerically going to modify them. So 0, 0 is row 0, column 0. So there's going to be a bomb. And row 0, column 1, there's going to be another bomb. So those are our 2 bomb locations. You can change them however you want. You know, maybe for this exercise, we'll do, let's do this instead. So then when we're doing part of our loop, it will make more sense to you. So I'm actually going to adjudicate this. And instead, we're going to make our second bomb. It's row 1, column 2. That's going to be our second bomb location. So we're going to have a bomb and a bomb. And then we also have to numerically represent these other spaces here, right? They're either going to be a numerical value that's going to represent that it has a bomb, how many bombs it has, how many cells away. So example, this one has 1 bomb, 1 cell away. It has nothing else here. If I had a matrix, if I had a 3x3, 1, 2, 3, 4, 5, 6, 7, 3x3 and 9 square matrix, and if I'm here in this cell here, this number 1, I only have 1 bomb, 1 cell away. Over here, I have 2 bombs at this moment. I have this guy here because I'm looking at this 3x3 matrix, if you will, to see adjacent cells. So I got a bomb here and I got a bomb here. So this would be a number 2. So this will actually be fun to do. So I'm actually going to change that to 1, 2 when we get back into the code. So like I said, we're going to come back in and I said we're going to do row 1, column 2 for this example. This is actually what we're going to run through our example. So this would not be accurate then. That's going to end up being here. Whoops, that will not be accurate. So we're actually going to take this out for now. So we're still going to return a 3x4 array. That's appropriate because that's how we defined it here. So let's make a little more space. And let's start this bad boy. I'm going to move the tablet for now, but we will be coming back to it momentarily because there's some good examples that we can utilize it for. So first, we're going to write out exactly how we defined our function. And I said we're taking 3 arguments, right? So we're going to be taking bombs. And that's going to be that first argument that we're putting through. Then we're also calling in our number of rows. And we're calling in, you guessed it, number of columns. We're going to close off that function. So we have at least 3 arguments. But in the bomb argument, we can have more than one row-column combination. So first we want to create a proportionally sized array filled with just zeros. So we know we have, in our example, we want a 3x4 array, and we want it to be filled with zeros first off. So we're just going to call it field. That's going to be our variable that we're going to create. And it's going to be a list. So, and we're going to do 0, because that's what we want to fill it in for I, whoops a daisy, 0 for I in what? In range of one of the arguments that we have, our number of columns, right? And then so we want to put a 0 for every I number of columns. Right now columns is 4, so we want to have 0, 0 in all of the columns. But then we also have to do that accordingly for... There's only one bracket at that point. For what? For j in range. Realize what we're going to do now here? Number of rows. We have to have the set number of the rows, otherwise we're not going to be able to do more than one row. Just do the 4 columns and we'd stop at that point. So this is just saying we're putting a 0. We're taking the range of the number of columns, and we already know we're going to have 4 for number of columns. We want to take that range, so 0, 1, 2, 3, and we want to put a 0 in any of those categories. And then for j in range, a number of rows is 3. So that's going to be 0, 1, 2. We also want to put a 0 in. So we're just doing, this is 2 different for loops in one line of code. If you want to see what that's going to look like, we could even just, and for argument's sake, we're going to get this guy already ready. So we're going to have Minesweeper. We have our function. Oh, I forgot an E. My mistake. And then within that function, we're putting in a list, and then we're doing a list of lists in the beginning. So I said we were going to do 0, 0 for our first bomb, correct? And then in our second bomb, we are doing 1, 2 for row column. Closing off that, closing off the first argument, comma, and we said we want a 3x4 matrix. Right, so let's run this and see what we get. So now, perfect. So we have, this is our, it's known as a list of lists here. If you want to print it more like a NumPy array, that's a different story. But we do have a 3x4, 3 rows rather, 1, 2, 3 with 4 columns, and they're all filled with zeros. So we kind of go, all right, sweet, we're on the right path here. All right, so I'm going to take that out just for now because we don't need that in our code. So now we want a for loop to take our bomb arguments and add them to the array that we just created. So we just created that array of zeros. We want to get our bomb locations from the arguments that we have into those locations. And we're going to do that with a for loop. So for bombs, actually, I'm sorry, we're going to do it as bomb location because that will make more sense when we debug everything in bombs. So for a bomb location in bombs, well, we're going to have to say what bomb location is going to mean, right? Well, we know that it's going to be the 0, 0, 0, and the 1, 2 that we have, so it's a row column, right? So what we're saying is bomb row. This is kind of the orientation that we have our arrays in at the moment. So we have our bomb row and our bomb column, and what does that equal? The bomb location. So now we're starting to get the format in place to what we needed. Now we want to update the field to show that the cell is a bomb, right? So how are we going to do that? Very simply, we're going to call field. And what are we going to do in field? We're going to change some of its positions. And we're going to do that simply by bomb row. That's going to be our first index position. And then, you guessed it, bomb column. And what do we want it to be? And we said we're going to make it -1. -1 is going to be a location of a bomb within this 3x4 array that we created. So just so you could see it, let's go back to field. We're going to print the field. So now we have our bomb locations. We said they were at 0, 0, 1, 2. So row 0, column 0, that's correct. And row 1, column 2, 0, 1, 2, that's correct. So now we have -1s where we wanted our bombs within our array. All right, so let's get rid of this. All right, so we're making good progress at this point. Now we want a way to select, we need a way to select all the surrounding cells. And I'm going to do this in a particular way with the idea of debugging in mind, because if I wasn't debugging, I would do this slightly differently. But I want to do it this way because I want you to be able to see exactly what it is that I'm going to be messing with. So we're going to call this first one row range. And what is row range going to equal? Well, it's going to be the range of the bomb row -1. And you're going to see why we're doing this in a second. Bomb row, and then we're going to add +2. Now this was so we could have a distance of 3 of the matrix that we were doing. If you recall on this picture here, when we were doing our imaginary matrix, we want to take whatever location our row range is at that moment. We want to create a whatever row, whatever cell we're at that point. We want to be able to do a for loop that's going to go through the rows and the columns to check the numerical value of that cell. And this is how we're going to do it in a way where we can easily debug it. So we're going to do the same thing for column range, and that's going to simply just be the range of what? Column, same thing, -1 +2. So that, I'm looking at that, I'm like, why is that? I like to have spaces in between my numbers. It just makes it, for me, visually easier to read. So now we have always selected our surrounding cells, the surrounding cells from the position that we're currently at that moment in time. So now we're going to do a for loop in the for loop. So now we're already in our primary for bomb location and bombs loop. And within that loop, we are going to now for I in what? Well, we want to first go through row range, right? We're going to go through our rows first. And I'm just, again, for the sake of debugging, current I equals I, so we can see it. I just want to create a variable so that we can see this. Now another loop inside of a loop. J is going to be tied to the column range. And same thing, I want to be able to see what that current J is going to be. Sorry. Just so we can see it as we're debugging. That's the only reason I have those in. Now, what we're doing is, as we do this for loop, so it's going to be for I and I, so for row 0, then we're going to have to iterate the for the columns, 0, 0, 0, 1, 0, 2, 0, 3, and then after we exit this column here, then it's going to go back to the original for loop and do row 1. And then inside that row 1 iteration, we're going to do column 0, so 1, 0, 1, 1, 1, 2, 1, 3. So we're iterating over the cells in a top to bottom, right to left fashion. And then, well, what the hell are we going to do in those cells? And again, this, when we debug it, or I'm going to write this out on the tab because it'll make more sense for you. What we want to do is, we have I, all right? So first we're looking at I, and we're also going to be looking at J. So what do I want to know? I want to know if I is less than the number of rows. Not only that, but I also want to know if I is greater than or equal to what? 0 in this case. It's going to make more sense now as we debug everything. So now this just says I, when it does this if loop, if I is greater than or equal to 0 and it's less than the number of rows. So we have our first conditional statement there. And it's going to get really fun. We have to do the same thing for who? Well, for the columns. And the columns are represented by J. And then they have to be less than the number of columns. So this is all we don't have to do. Yeah, that's going to be fine. I closed it off. Go away. And 0. J is less than num columns. All right, I'm just making sure I have everything where I need it to be. And if you haven't followed, the num rows and num columns is where it's up here in our arguments. So now what are we doing in that if loop? If we find that condition, we're not just stopping there. So we have if, end. I actually didn't want to close that off just yet. Why? I'm adding another end. So what we're going to be doing is we're going to be finding if we're in the proper row column location, and we want to make sure that there's no bomb in there at that moment, right? So how are we going to do that? Well, we already know in our field where the bombs are. So we want to make sure that the field is not, that the ij that we're currently iterating through, we want to make sure that it is not equal to a bomb. That's where our -1 is going to come into play. So we're going to need a true and a true and a true in order to execute for the next loop. And what are we going to do if we did find this condition? Well, we want to update that cell in the field. And again, we're at the ij cell is what we're trying to do. And we want a plus or minus 1. We want to up that index. That's all we want to do. I'm missing. There, that's pretty now. We just want to update that particular cell of the field. And then when we're all said and done, we want to return our field that we created. Make this a little tighter here. So what we just did with that particular code, we're going to iterate through the row columns, and we're saying if the row is greater than 0, so let's say I'm in here, it's greater than or equal to 0, so that would be true, and column is greater than 0 and less than the row cols, the number of cols, which is true because it's 0 and it's greater than or equal to 0, and it's less than 4. So we have a true and a true, and the field ij, which is 0, 0, does not have a -1. This does have a -1, so this would be a false, and we jump out of that loop and go back into our for loop until we got to a true. So this would become a true, and then with this being a true, it would also say there's no bomb in here. This cell, the row is greater than 0, it's less than 3. The column is greater than 0 and it's less than 4. We don't have a bomb in it. The field ij, which is field 0, 1, does not have a -1. So then what we're going to do is we're telling it in this field, update it to +1. So that would simply then take this and make this a 1, which would tell the player at that point that there is, from this cell, there's one cell around here in this 2 by 3 matrix that has a bomb. And of course it's right here. And then as we go through the code and we get to here and here, this would in reality become a 3 because there's 3 bombs within this cellular matrix. And again, its cellular matrix, just to separate it, would be here. And theoretically it would be up here, but we don't have any cells up here. So this particular cell has a bomb here. We have a bomb here. I'm sorry, I thought this was also a -1, so I'll make it that way. So then we would have 3 in this number telling us that 3 of its 6 cells have a bomb. All right. If you're not confused yet, good. Let's debug. All right, so it looks like it's going to run. Let me see what I get first off if I run it. Let's see what my output is. -1, 2, 1, 1, 1, 2. -1 would be here. That's why that's 2, because I have a 1 and 1. All right. And then you have an adjacent bomb. Yes, you do. My third row, 1, 2, and 3 should all be 1s. They're all 1s because there's a bomb. All right, cool. So it looks like it's appropriate. So let's do our favorite thing. Let's run this debug. I'm going to F8. We're going to hit our print function, go back into our function, and we have here our bomb class list, which was just our input. Let me bring this down. Our field. This is where we did the 0 for I and range for the number of columns and J for the number of range. We're just creating our matrix filled with zeros. So it did that appropriately. That's annoying. I wanted to see that. I wanted to bring, just so you can see it here. So we have our 0, 0 matrix there. Now for bomb location and bombs, so we're going to go bomb locations right now. It's a list and we're at 0, 0. Where did it get that 0, 0 from bomb location? It got it from our first argument. Our first argument here is bombs, and we have 2 within that argument. Now we're just breaking down the bomb location, that 0, 0, breaking it down into a bomb row and a bomb column. So we're going to get bomb row and bomb column. We have a 0, 0, that's appropriate. Now the field, we want to update the field. We want to tell our field, hey, we know where there's a bomb. There's a 0, 0 bomb. Right now our field, as you can see up top here, is simply just all zeros. So we're going to update it with a -1. Meaning what? Again, we're telling our field now, where there's a bomb, make it a -1. And you're going to say, well, it didn't do it for 1, 2. Well, no, because we haven't gone through that bomb location yet. We're still going through the code. For bomb location and bombs. That's true, that's true, that's true. We're still within this for loop. When we jump out of the for loop, then it will go and look for another bomb location. So now we're just going to create row range. And I just want to quickly say, before I even go through this, I have for I in row range. This row range could be taken out and you could put this code in there and it's the same thing. I pulled it out of that for loop because I wanted to actually see the variable produced in memory so that I have something I can visually track as I'm running the code. So row range is simply the range from the bomb row -1 to the bomb row +2. So we have a row range -1, 2. And then we have our column range -1, 2. Totally, that's appropriate because we're 0, 0 at this point. 0 minus 1 is -1, and 0 plus 2 is 2 for both of our row and our columns. Now I'm just going to quickly jump over here for a second to show you what this is going to be. So we just did a range. What did we get? We got -1, 2, so that's appropriate. So -1, 2, I just want to run this to show you what the output's going to be. Let me bring this over so you can see the output. Actually, no, I can keep it like this, and I can... I didn't mean to do that. Let me bring it up to a float window. So we have a 0 and a 1. Why? Well, because I'm printing out the I for the range of -1 to 2. We're only getting 2 values within that. So what happens if we make this a 3 for I in range 0, 1, 2, 3? We're still getting a 1, 2. If we made this a 0, and that's not proper, so I had to make this bigger because we were getting the wrong answer. So if we were 0, we'll go back where we were. What was it originally? Let me move you for a second. -1, 2, -1, 2. So if we run this, we should get a -1. Because, okay, perfect. So we have a -1, and then we're going 2 numbers. Index is 0, -1. So we have -1, 0, 1. That's for the I in range of 1, 2. If we increase this to, say, 5, we're going to get the -1. It's still going to count up to 4, which is going to be 5 numbers of the range, 1, 2, 3, 4, 5. And conversely, if we did it to -3, then we would have 3, 2, 1. So this is why we're not having a problem with calling cells that are outside of our actual matrix. Because it's not going to, these negative numbers are going to just simply equate to less than 0. So it's not going to be an issue. All right, so back to the code. So F8ing through, for I in row range, and I just want to show you what that I is. That's why I have that current I equals, and that current I in the row range is -1. Why? Well, row range, the first I is going to be -1. That's appropriate. For J, what do you think you're going to get? You should get the same -1. So we have -1, -1. So now as we go through this piece of code here, this is exactly what we're going to be looking at. We're going to have -1. I'm going to do it one time on here, and then you can do it for the future times if you like. So let's clear this out. Let's, whatever, that's fine. So we had -1, -1, correct? Yeah, -1, -1. So if we're rocking OCD, so we have I is -1 and J is -1. All right, so this is our row and our column piece that we're playing with. So if you follow this with the code, what are we saying? We're saying if 0 is less than or equal to -1, and -1 is less than the number of rows, which was 3. Well, that's true. Is -1 greater than or equal to... No, so this is a false. So right there, that code's going to cut out. So we can see what's going to happen is we're going to run right down into the j. And if when we try to run through this loop here, it's not going to go. So I'm going to F8 through there, and we're going to go back up. Why don't we go to I? Because we're still in the first row. We still have 3 more values in the range to go through. So now j is going to turn into 0. Why? Again, because we were at -1 to 2. So it's going to go 0, and then after that, I guarantee you it's going to go 1. And then we'll go to the next row. So now we are -1, 0. Let's see what's going to happen. So if we're hanging out here at -1, 0, so let's do it. We'll just for fun. All right. So now we have an I is -1 and j is 0. So is -1 greater than or equal to 0? No, I'm still at a false now. It doesn't even matter what j is in either of these examples yet. In our for loop, we're still getting a false, so we're not able to proceed within our code. So I'm going to be pulled out of that loop. Now go back into j, and now j is going to be a 1. So now I'm -1, 1. This is the last cell of the first row. So now we're -1, 1, and you should know the answer to this. I'm not even going to change the damn color, because now if I'm I -1 and j 1, it did not matter what j is yet, because we have not even gotten a true statement yet on our I, because our I was... In this case, it was 3, the number of rows. So we have not even gotten a true on this. In order to get a true, our I has to at least be 0. And we haven't even gotten a 0 I yet. So let's see what's going to happen. And it should go, F8 through this, back up to 4i in row. It jumped here and it saw that there were no more in the range for column range. So it went to the I range, which is appropriate. So we're going to F8 through there, and the current I is going to change to 0. That's appropriate because we'll go -1, 0, then 1. And that's going to be our 2 values starting from the -1. So now we're at 0. We have to F8 to change our column. That's going to be -1. All right? So appropriate. So now what's going to happen, and you probably might have guessed it, now we're 0, 1. So we're going to, let's clear this layer. So now we have our I is 0, our j is 1. No, wait, 0, -1. I was going to say, I think that's wrong. -1. So now our I, this is just how we're going through the code. So now we're at 0, has to be greater than or equal to 0, and it has to be less than 3. So I have a true. But then I have end, -1, greater than or equal to 0, I'm at a false right there. So I'm already jumping out of that code. So until j gets to a 0, I can't even go any further, right? So you're going to see it better jump out of this. Good. Now we're talking. Now we have an I of 0 and a j of 0. So let's see what we get within this code. All right, so now we have an I of 0, we have a j of 0. So we have 0 is greater than or equal to 0. That's a true. And it's less than 3. Sweet. So we have a true. And 0 is greater than or equal to 0. That's a true. And it's less than 4. I have 2 trues. But I'm not done. I also have another end. And the field for ij, which is 0, 0, that's my row column, right? Cannot equal -1, meaning it cannot have a bomb there. Well, let's look at our field. At 0, 0, do we have a bomb? So if we go to 0, 0, do we have a bomb? Row 0, first row, column 0, -1, son of a b, we got a bomb. So what just happened to our code? What you should have somewhat presumed, which is now we have a false. So true and false equals false. So we're jumping out of that code. We're not able to come back into that code. So now we got to jump out. F8. Now we're going to be at 0, 1. And just for before we even get there, let's quickly look at our field and look at 0, 1. Row 0, column 1. It's a 0. So we do not have a bomb in that location, right? Awesome. So let's see what this should do for the math. So we have a 0, 1. All right, bring this like this. Let's clear out the level. All right, so now we have I is 0 and j equals 1. I'm anal retentive. I'm going to make sure it's right. All right, good. So we're right, 0 and 1. So we saw before that we have, 0 is greater than or equal to 0. That's true. And it's less than 3. So I have a true for my first. And 1 is greater than or equal to 0. That's true. And it's less than 4. Sweet. And the field at 0, 1 does not equal a bomb. I got a true. So now I got true, true, true. So then, oh, looks like boobs. So then we can go to the next line of code. And the next line of code that we're going to have is going to say we're going to take our field at, where do you think? Location 0, 1. That's my I and my j. And I want to do plus equals 1. So what's going to happen now in my row of rows, I'm going to have a bomb, and then this should be a 1. Right now it's a 0, but it should update to a 1. And then it should go all the way back and then run that code again. So let's see how we're doing. F8. Now, good. We got to line 30. That's our field, ij equals. And then you can, I'm going to see if I can make it like this so we can watch. Here we have -1. This 0 should turn to a 1 on the next execution. And the bastard jumped on us. -1, 1. There we go. So we have our 1. So now we know that in this cell, the represented cell of row 0, column 1, that if you were to click this cell was exposed. It's going to say a number 1, telling us that one of the adjacent cells, we're not calculating above, obviously, because we're row 0, has a bomb. All right, so that was successful. Now, I'm not going to keep going through this for each location. I just wanted to do that for observation for your own self. But now that you're going to see, we went through range -1, 0, 1 for column. As we're done, so now it's got to go to row number 2, which is index of 1. So when I FA through there, it's going to change now. Now it's going to start going through this row. We're going through that row at this point now. So let's go and start going through. 1, -1, 1, -1, 1, 0. Up. So far we can see based on that we're getting executing codes that we were able to adjudicate, and we got another 1 on our list. So I'm just going to go through all of this. Now you can see bomb location. It went through all of the rest of the arrays. Bomb location is now going to change because we ran through the 3x4 matrix for this location. Now we're going through the matrix for this second bomb location. Same exact thing. We're going to run through this for loop. Come on, baby. 1, 3, 2, 3, 2, 1, 2, 2. 2 should take us out of a loop. There's no more bomb location. So for bomb location and bombs, we're done. So now we're going to jump out of that final loop and be to return field. And if I F8 through that, we're going to come out and we're going to be given, let me bring this up. There we go. So now we can see where we put our bomb locations in. These are the -1s. And then the 2, the 1, the 1, the 1, the 2, the 1, the 1, the 1, the 1, the 1. All those 1s and 2s were controlled by this for loop. Well, what we were doing is, in the whole point of that loop, again, we were trying to find where the bomb locations were so that if I expose this cell, I know that I have 2 bombs that are nearby. So if I brought this out, I'm just trying to make this as visual as possible for you guys. Let me do this. Let me bring you up. Clear layer. Oh, whatever. I'll draw the matrix in this. So we did a 3. All right, so we have this, and of course, I'm not going to draw it, but we have our rows, and I'll just do this. I'll do row 0, row 1, row 2, column 0, column 1, column 2, column 3. It's nice and bright. So now what I want to do is, let me get rid of this guy. We are -1, 2, 1, 1. -1, 2, 1, 1. We are, one second. Let me bring this, where's my pen? 1, 2, -1, 1. Going backwards. All right, so this is what our matrix ended up filling out. Remember, we started with all zeros. And then after we started with all zeros, then we put in our bombs with the -1. That was a simple just rearranging within our list of substituting new values from our argument. So now we had these guys in place, and then we did our for loop. And when the for loop was going through, again, we went 0. It started at 0, and then 0, 0, 0, 1, 0, 2, 0, 3, and then it went row 1, 0, 1, 1, 1, 2, 1, 3. So that's how it was going through the cells. And when it's going through the cells, what it was doing was it was trying to find those end, 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 if we had all three combinations appropriate. So in this particular one here, remember, it was started as a 0. And the first time we went through it, we turned it into a 1 because we got to a point where row 0 was greater than or equal to 0 and was less than 3. And column 1 was greater than or equal to 0 and it was less than 4. We had true and true. And there was no -1 in this cell that was true also. So we upped it to 1. It would change to a number 1. But then what happened when we went through this row, we went through row 1, and when we got to examining this particular cell, because again it's going to iterate through the loops yet again, this was going to end up getting changed to 2, simply because now it had this number right here is represented by this cell, this cell, this cell, this cell, and this cell. So this particular cell, in its neighbors, it has 2 bombs. This cell, it only has 1 bomb in its neighbors, because we're doing, depending on the cell size cells, 3 by 3. Because if this did not have 1, I'd be checking here, 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 and here, 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 and here. But that's what the iteration on our for loop was doing. And you may sit there and say, how the hell... I did have a student once ask me this. How did... let's make it a little different. How did... If this was originally 0 and we got to 1, like they understood that part. They understand how we got to a 1. But then when we got to this row and we came and we got to this number here, we got to this cell here, how the hell did the code know to back to essentially space 0, 1 and change it from a 1 to a 2? Well, you have to remember when we first did this, when we first did the first row 0, row 1, row 2, this was not yet here. It was only after we finished all 12 cells that then we went back up to the original for loop for bomb location. And then bomb location then changed this cell to a -1. And then it goes again, 0, 0, 0, 1, 0, 2, 0, 3. And when it got to this location here, when it was doing its check, it found that it did have a bomb location. It did have an end and an end and an end and an end and an end. And so it adjudicates itself up to a 2. That's all that happened there. If that's not clear to you, let me know. But that's how we got it. Essentially, when we ran through this loop the first time, then we came back up to bomb location and bombs, and then it put in this second location of the second bomb. Then it went back through this for loop yet again to adjudicate what it was a 1 into now a 2 based on this parameter of the code here. So pretty involved. Granted, I'll give you that, but an excellent exercise, not just in Python and for loops and nested loops within nested loops, but even in how you can do, like, I think this is a really fun piece of code here. This particular line right here, I thought that was really good. And it's a great way to make it visual. I think this was a great, let me get rid of this guy. I think this was a great piece here. I like how we got to use one word argument, bombs, but we were able to pass a list of lists for that one argument. So even though we have 3 arguments, it's taking 1, 2, 3, 4 different parameters, if you would. Pretty cool. So then if you didn't put this as a list of lists, then you should get an error. Yeah, perfect. So we're going to get an error. So that was good. Glad to see that works. That would be for you. That's for you. Oh, that's why I have to... If I did this, we should get a different error. Yep. See, it takes 3 positional arguments, but we gave 4. That's because we, as far as we know, we gave it 1, 2, 3, and 4. So we want to encapsulate this entire list of lists as one argument. So then when we run it, we'll get the appropriate output. Given an array, what is the most frequently occurring element within that array? So this is going to be done in linear time, so a big O of n. Essentially, what we're just going to do is create an empty dictionary to keep track of the occurrences, and then we're going to return the element with the largest maximum count. So nothing too monstrous today. So we'll call it most frequent, and what are we passing? We're going to pass through a list into this function. Of course, we want to create our count. Like I said, that's going to be an empty dictionary. All right, so the empty dictionary, we want a key value for the count. And we're going to set our max count. We'll set it to 0 for right now. We're just initializing max count. That's going to keep track of the number of times each item has occurred. And then we're going to have a maximum item, which as of right now, is going to equal none because we don't have any. The max item is just another variable. It's going to keep track as a counter in real time for the most frequently occurring item that we have thus far. So for I in list, we're just going to iterate through the list that we're given in the argument for the most function. If the I is not in the count, well, what do we want to do? If the I, for I not in count, we want to index we want an index item that has not been saved yet. That's what that is for. I have not in count. If it's not in count, count right now is empty. So if it's not in count, we want to do something with it. We want to index it. We want to put that element in count, and that element's going to be I at that moment, right? And we want to give it a count of 1. So we want to actually, whatever the element is, if this list has an element 2, and if there's no 2 in count yet, then we want to add 2 to this empty dictionary called count. Else, so we're going to jump down, and we're going to throw our else in. This means we have to see, we also have numbers that we've seen before. So if we've seen the number before, what do we want to do with count? Well, we want to add to it, right? So now we have a way that we've seen the number before. We can add 1 to its value in the dictionary key. But what if, not what if, but rather we also have to, we're also going to have to, I'm just trying to make sure we have max count, max item. So now we have to go through our max count and max item and see if they need to be adjudicated as we go along. So the this will make sense. If count of I is greater than maximum count, this is comparing the value of the elements in the dictionary to the maximum count. So whatever value in the dictionary we've built in this loop, we're comparing it to the max count for that particular I. All right, nothing monumental there. So if the max count of I is greater than max count, we want to update max count because it should be the maximum count, right? So we want it to be the count of that I so that it updates maximum count. We want the maximum count to reflect the maximum count for that particular key in the dictionary. And then, of course, we also want to update if it is so, it's the new king of the max location. So if max count is updated, then that max item is also going to take the cake for right now. So all of this is doing is just updating these 2 variables here as we go along, iterating through our list. And then simple as sweet, we want to return what? Not the max. Whole point of this is to get the maximum item, right? Given an array, what is the most frequently occurring element? We want to return the max item. So no errors showing up yet. We have call our why are you? Oh my goodness. I really should have my coffee first, shouldn't I? we're going to open and close, and I'm also going to open and close the function out just so we're consistent. And now within this, we're going to be passing a list. I'm going to put that list in. So let's say we did 1, 3, 3, another 3, 2, 1, 1, 1. So we can tell that we should get a 1 as our output. But I wanted to have the 1 after the 3 because I don't want it to be numerically validated. And you should be able to do negative numbers in this as well. So let's see what we're going to rock here. So we have a 1. All right, so that worked. All right, so we can debug through this. I'm just going to argument's sake, I'm going to increase it to 3 and run it again and see if we get 3. Okay, cool. So let's close that out. I'm going to get rid of a 3 so we can keep it at 1 because I like the idea that it's value-wise is less than a 3 and it's after the 3. So make sure that we're actually iterating properly. So let's debug through this bad boy. Not going to need you. We're going to go down to our print, get our list. Now we have our list in memory. Count is an empty dictionary in memory. Max count's a variable set to 0 in dictionary. Max item is set to none. Now we're going to iterate through the list. So I is going to be 1 because that's our first element in the list. If I is not in count, count right now is empty, so it's not in count, so that's going to be true. So we want to increase that to 1. So now it's going to say 1:1 because it's a dictionary. So now we have one occurrence of the number 1 so far in our count. And then we're going down if count I is greater than max count. Well, max count is 0, so that's true. So it should update the maximum count to 1, and the max item we're going to update to whatever I is at that moment. I right now is 1. So now we have our king of the hill is max item is 1. Now we're going to go through the next number, so it should be 3. So we're going to go through 3. It's going to add it to the list. Max count is greater than max count. Nope, it's 1. So 3 has an occurrence of 1. 1 has an occurrence of 1. So there was no update to be done. Now we're I in list. Now we're going to know we have the number 3 again. So count was in there, so now we're going to hit the else loop. So count, just increase it by 1. So this 3:1 should become 3:2 when I go through this line. Excellent. If count I is greater than max count is 1. Count of I right now is 2. So this max item here should change to 3, and the max count should change to 2. 2 and 3. Excellent. And all we do is update the max count to be count of I and the max item to be I. And we're just going to keep going through this. We have 3 again. Now we have 3 3s. So the max count was updated. Max item was already 3. Now we have a number 2, but number 2, which was never seen before, so it created the key value of 2 1. But it did not. The max count right now is 3. So 1 is less than 3, so it didn't have to go through this code down below. And we're just going to keep going. We're going to get our 1s. Now we have 4 1s. So now max item right now is set to 3. Max count is 4 because I1 is the 4. So max count 3 should change to 1 right now. Excellent. So now that we're going through this, let's see. So we went through the whole for loop. Now we're just going to return the max item. And that would have been the number 1, which we have. Let me go to floating mode. I should just do that automatically. Which we have is the number 1. And if we wanted to make these, the negative's not going to make a difference because it's checking the occurrence of each particular element. It's not checking the numerical value of it. So you can see that we have -1 as the return. So another quick function just to show us how we can utilize lists, for loops, iterations, if loop, else loop, and just creating some variables inside that will create a counter. So you'll notice a lot of what we'll be doing in a lot of our array problems, we're creating counters or creating pointers to iterate through arrays, or we're creating counters in dictionary style. So we have a key value count to go through this. Equally enough to find the least occurring element in a very similar fashion, which we've done before. So we have most frequently occurring element, and we've done least as well. And this one's going to be based on strings. Now remember, strings are going to be different than arrays. Arrays are easily mutable. Strings are immutable characters, so or rather elements, so we have to do things a little bit differently. So this question, given a string, are all the characters unique? So we should give a true or false return. First, I'm going to show you how you could use this just using Python built-in structures, and then I'll show you how we could create our own lookup function. First off, we're going to define what unique is going to be, and what are we passing through? Nothing more than a string. You could even write string if you want. First thing I'm going to do I want to replace spaces. So let me first show you what I'm going to be passing through. All right. So when we're done with that, when we're done with the whole thing, I'm going to be passing through the following string: A space B space C D E F. So we're going to be passing again if all the characters are unique. But I have these spaces in here because I don't like when people just do like, you know, A B B C. It's not reflective of what you do in real world. In real world, you're going to have spaces, you're going to have capitals, you're going to have lowercases, and it's a good idea to understand replace methods, lowercase methods, and so on. And you're going to see me use it a lot in a lot of the algorithms that we use. So I just want to get rid of any spaces that are in there. So to do that, we're just going to reassign what string is going to mean, and I'm just going to tell it I want to replace it. So we're going to dot replace method. What do I want to do? Well, I want to tell it right now there might be spaces, and I want to replace it with no spaces. All right. So that's what we're doing there. We're just going to fix that up so string is a little bit cleaner. Now, the easiest way to do this using Python built-in structures is with a set. And remember, a set is an unordered collection of unique elements. So it's giving us unique elements. It's just not going to be ordered. We don't care about order. So therefore, if we can create our string that is going to be in a set, then it's very easy to see if, comparing the length of it, if it's going to be unique or not. So all we have to do at this point is do a return. What are we returning? I want to return the length of set string. Whoops a daisy. So we're creating a set of the string, and I want to know, is it equal to the length of the string? Am I on unique? I'm on unique. Let me drop this down to a floating window. So it tells me true. So remember, whenever we're doing anything with parentheses, always work from the inside out. So this operation is going to be done first. It's going to create a set of our string, which is the string is the input. Again, remember the string, we took out the spaces. So actually, let's do this. Let's debug it as we go through it. Nope. I wanted to run debug. Yep. I'm not going to need anything else. That's fine. So it's going to put our unique string into memory. And we can see we still have our spaces are held intact. And we're going to get to this next line. As we execute line number 9, it's going to replace the spaces. So you can see in memory, now we no longer have spaces within our string. So now we're take a set of this string. This is already ordered. So it doesn't make a difference, but a set is unordered. So take a set from our string, which is going to be exactly this, only unique elements. So we'll do repeats in just a second. And then does that equal the length of the string? Well, the length of the string is 1, 2, 3, 4, 5, 6. And how many unique elements are there going to be in this? A set of the string is going to be 6. So does the length of 6 equal 6? Does the length that's equal 6? Yes, it does. It's true. So it's going to return true. So we'll finish just debugging this so you can see that was going to be it. So let's mess with it. Let's put a non-unique element in. So now I get a false. Why? I know you're going to say because the B is redundant, and that's true, but let's see what's going on in the code. So we have our string. String's going to take out the spaces. So now if you wanted to see a length of the string is what? 1, 2, 3, 4, 5, 6, 7. So that's equaling 7 right now. The length of a set of that string. Remember, a set is an unordered collection of unique elements only. Well, this was 7 for the length of the string. How many unique elements do we have? 1, 2. We're skipping that second because it's not unique. 3, 4, 5, 6. So does 6 equal 7? False. So that's it. It's a nice quick way you can use built-in Python structures for that operation. Now, we're going to do the same exact problem, find the unique elements, but without using Python built-in, without using Python built-in functions. So the way we're going to do this is the same thing in terms of define unique. We're going to pass, we'll just call it S for now, so it's easier to type. We're going to define the function unique, and it's going to pass a string through it. And just like before, I want to replace the spaces with no spaces. Because again, the inputs are going to be, I want to make this a little bit more real life. And then what we're going to do is we're going to take our characters, we're going to make a variable characters within the element, and we're going to put them into a set. Now we need to iterate over this string to see what we're going to add into, remember, we only want to add unique elements into this set. And again, yes, it will be unordered. So for letter in S, whoops-a-daisy, we're going to iterate through that string that we're putting through. So again, just so we have a mental idea of what we're doing. And the string that I said will pass, what did we do before? We did a space, B space, C, D, E, F. So we'll pass our string, which right now we know has all unique elements, so it better be true in terms of the return. So for letter in S, we're going to do now the if the letter in characters, if it's going to return false or if it's going to return true. So for letters in S, is that in characters? Because remember, characters is a set at this point. And if it's not, then we want to do something with that. So if letter in characters, and right now it's an empty set, nothing to, we want to return false. Because if this is going through, let's say we had this, BB. Well, as it goes through the code, we're going to do an append in a moment or add it to the set. Imagine there was an A and there was a B. When it gets to this second B, if the letter is in characters, B is, well, that's true. Then we want it to return false because then it's not a unique pair of elements. So what do we want to do with that if there is nothing in characters, if that particular letter or element is not in our character set yet, what do we want to do? Well, we want to add. And what are we adding? We're the letter, because that's what we're iterating through. It could have been I or S or whatever you wanted to put in to identify your iterator. That's what you would have done there. So characters.add letter. So now if it does not exist within character set, we're going to be adding it. And then when we're done with that loop, when we're done with the iteration, we're going to return true. Because if we did hit a repeat letter, we already are going to be stopping here at returning false. If we do not hit any repeat letters, then we will return true. So let me see. Unique, I got a false. Oh, because I put a BB. So we return to false. If I take out that B, I'm going to run it again. I should get a true, good. Let's take them out of sequential order. Out of alphabetical order, rather. Let's do LKJ. RW. So we know that these are all unique characters. So we get a true. And if I replicate one of them, I'll put a J over here. And we should get a false. Awesome. So let's just quickly run through a debug on this. So we can say we were thorough. F8 through it. And get this out of the way for a second. So you can see in memory, we put our string into memory. We're going to replace out the spaces. So we just have a set string. Characters equals a empty set. So we're going to have right now in memory. So for letter in S, S is our string above. Up here, for letter in characters. So we're going to F8 through it. So it's going to take the first letter, which is I. If letter is in characters, right now characters is empty. Return false, but that was false. So we're going to skip that and jump down to the next piece. Otherwise, characters.add letters. Well, right now letter is I. So we're going to add what? Characters.I. So when I go through this, it should add I. Wonderful. And then it's going to go through L. If letter in characters is not in characters. So we're going to jump down to our else statement, which is characters add. So we're just adding these individual elements. And let's get to a J. There we go with the J. And you will notice that, where am I here? I want to get to that second J so you can just see how, oh, damn it, I missed it. There's J. And remember, again, a set is an unordered pair. So we're running it this time. It's a different order than it was before. What are we now? We're on E. So the next letter is going to be J.
So now we're on J, but look in our character set. We already have a J right here. So if letter is in character set, well, that's going to be true. It is in character set already. We're looking at J right now through this iteration, and it is in the character set. So what are we going to do? If this is true, we're going to go to the next part of that if loop, which is going to be return false. So return false is now going to be executed. And sure enough, in our output, we'll be given a false because it is false. And if we took that out, then going through it, same thing, we're going to have it replace it out. It's just going to run through the characters for each individual letter, and it's never going to find, it's going to always find that every letter is unique, every element is unique. It does not find it within the character set that we created. So we'll end up returning true at the very end of it all. Non-repeat elements. So we're taking a string and we're going to return characters that never repeat. If there's multiple uniques, it's going to return only the first unique. And then after this is done, I'm going to show you how you can return every single element that is not repeating. This has huge implications in security. So for those of you who are like, well, am I ever going to need this? So what is it? Not only is this great practice for Python and for algorithm learning for interviews, but this is also very applicable to data security. So let's jump in, and not to mention this is also a linear time solution. So what? So we're going to do non-repeating. That's what we're going to name our function today, and all we're passing through that is a string. Now from the last video, if you remember, the first thing I'm going to do with any string that I'm messing with is we're going to replace what? Spaces with no spaces. And on top of that, I want to make this all lowercase. Just otherwise, if I didn't have it lowercase, a capital A and a lowercase a are different elements. So if you sit there and say, oh my God, it gave me back an a big A and a little a, and you say those are not unique, those are the same, but they're not the same, they are unique. They have very different binary codes, so they are unique. So we're just going to make everything lowercase for simplicity's sake. Now, how are we going to even do this one? Well, we're going to create a dictionary. And again, the dictionaries or hash tables, depending on your language, they're all going to track the key value pair for each character in the string. So we're just creating a count. You know, it's not very different from a lot of the stuff that we've done, just done it a little bit different way. So we're going to create a character count. And again, that was just going to be at this point an empty dictionary. All right. Now, for character in S, or for CNS, we'll keep it nice and simple. What do we want to do? Remember, you guys have seen this all the time. If the character is in the character count, then we can add 1 to it. If it's not, then we want to add 1. So what does that mean? Okay, well, we did for character in S. If character is in character count, if it's in character count, then I want to take character count and I want to add 1 to it for that particular element. Oh, so I need to do, I almost made a boo-boo. This is for that C, only for that letter C. I want to add for that particular iterative element that we're using at that moment, which in this case is C. For character in C, if C is in character count. If it is, then we want to, for that particular C, we want to add +1 for that value. And then, of course, we always have the, well, what if it ain't? So then we're going to have to do our else. So if character is not in character count, then what do I want to do? Well, I just want to simply take character count and for the particular C, don't forget that part, and we want to add it there. We want to give it its first value of 1. Now we're going to iterate again, and then we're going to do a second iteration to return the characters with only 1 count, meaning the unique character. So how are we going to do that? Well, still within this function, but we're going to back out because it's a whole separate for loop, if you will. For C in S, so same thing there. If character count for that particular C, because again, we're iterating, so we're going 1 by 1, equals 1. If it equals 1, that means it's unique, right? So we want to return C. Come on. Otherwise, if I'm going to back out of this, I'm going to return none. Come on, man, stop that. I want to return none, otherwise, if none of them are going to equal 1, which means that if there are no repeating elements within that particular string, then damn it, I want it to tell me so. So
let's do this. We named this non-repeating. There we go. It's a string. So I'm going to put quotes inside that function string. And we're going to do I, apple, ape, peels. Now I did this on purpose. So let's run it. Run non-repeat. Again, let's make this a floater. There we go. We got a floater. And it returned I. So is I the only one that's not repeated? I is not repeated. A is repeated. P is obviously repeated. L is repeated. E is repeated. There's no other unique. So that is appropriate. Now, just for argument's sake, what if I want to prove a point. If I do this and if I take this out, later it will give me all of them. See, now first it's giving me a capital I. It's only returning the first one though, but it would have also, and the reason for that is, as it goes through this loop and it creates the counts for the dictionary, when it goes through this and it gets to the letter I, because that's the first one that it's coming across, if the character count equals 1, that one does. So it's going to return C, and it's going to completely take me out of the loop at that point. It's going to stop going on. But you're going to see later how we would have to, we would get multiple returns for unique elements. And I'm going to take the lower out just to show you what it's doing. So let us, we'll debug it real quick. Even though I think the next one, the debugging is going to be a little bit more appropriate. So let's debug it. I don't need this. So let's F8 our way through. We're going to put our string into memory. I, apple, A, peels. S.replace, nothing new there. It's going to lowercase and it's going to remove all the spaces. Character counts an empty dictionary. So now for C in S. So its first one's going to be I. For C in character count is going to equal C. So now right now the C is I. So I is not in the character count. So it's going to go down to my else. Else, make it 1. So now we're going to have an I and a comma 1, or colon 1, I'm sorry, because it's a dictionary. It's not a tuple. So now for C and S, now we're going to go to A, and it's going to do the same thing. You're not in there, so we're going to go to the else. We're going to go to an A. We're going to go to P. This is the first time it's seeing P. Now we're going to P again. So again, we're at the second P in the word apple. For character in character count, it is. Right now, P is right here and it has a count of 1. So all I want to do is go to the next line of code because that was true. Character count of the index C at that moment, which is P, equals whatever P is right now, 1 plus 1. So it's going to change that to 2. So now this is how we're getting non-unique elements. And as we go through this whole loop, wait till we get to the L. We have our L. So next is going to be S. S is not in there, so it's going to add a character count of S1. Excellent. Now we're going to jump into this for loop. You're going to see that it's going to try to find a for C and S, but all the C's are done. So we jump into that for loop. Now we're down below. For C in S. If character count equals 1, so we're going to FA through. If character count equals 1, well, the first C in S is I. I equals 1. That's going to give me a true. It's going to go to the next line of code, return C. It's going to return that I, and as far as the code is concerned, it's done. But we know that that is not true. So there we go. We have our I. Because we know that there could have been other letters that repeated. And if it wasn't the first letter that was the unique element, then when it got through this line here, line 21, it would have went to 22. When we executed 22, it would have skipped this and it would have returned not at that moment. I'm sorry, no, I'm lying. It would have went back to the for loop and it would have done the second C, which at that point would have been the A. And it would have been looking for the first time that character count equaled 1, character count being that dictionary we created for the key value pairs. So what would we do to this? Get rid of that for a moment. What would we do to this if we wanted to make this account for all of the non-repeats? Well, to do that, we're going to sit within the code that we've already started. I'm just going to bring some of this together so we have a little bit more space on the screen. So what would we need to change if we wanted to return not only the first element, but any and all, a total of the unique elements? Well, let's go line by line. So we can obviously keep this. We can clearly keep this. There's no change in there. Character count still going to be empty dictionary. We're still going to be able to keep our first for loop. Let's actually do this. So a little bit of separation visually. We can still keep our first for loop. There's no reason we have to make any change in that. We're still creating a dictionary with the characters and the count for that. But now it's going to get a little bit different. So what we're going to do is we're actually going to get rid of this second for loop. And what are we going to do instead? Well, we're going to create a list. So to do that, we want our final answer. And it's going to be, at this point, an empty list. All right? Actually, let's rename this. Let's call it all uniques. So we're going to make a list of all the unique elements that exist within the string that we're putting through. So we have an empty list. We want to sort our dictionary now so that the values control the order of the keys. And we're going to do this in an ascending fashion. So a nice little quick way to do this is we're going to create a variable y, just so we have something to plug this object orientation into. We're going to take a sorted. So we have sorted. And what are we sorting? Well, our character count that we have from above. And we're sorting it by the items that are within inside of it. Now, by doing this, that's not right. That's better. I'll add, because I do want to add one more piece to this. So we're taking our dictionary that we created, and we're sorting it based off of the items that are within that. That's going to put this in an ascending, meaning the lowest count to the highest count of the elements. So it's sorting it for us. Now, with something else we're going to be doing is we're going to add a key lambda. Key equals lambda, and I'm going to say at this point x, and I'll get to this in just a second, x1. And of course, so, oh wait, no, I don't want to reverse it now. I wanted to show you that part later, because right now I want ascending, right? Yeah, we'll do ascending. So lambda is, it's something we haven't covered before, and I'll cover it in another time. But lambda is a way of almost like doing this whole defining of a function piece. It's a function of itself, and it's going to carry out whatever that function is that we're specifying at that particular moment. So all we're doing is we're saying we want the key to be that second position, because the first position is the key, the second position is the value. And we're looking for this x1 that we're going to be executing. And then what we're going to do is we're going to compare the index 1 position of each tuple, because again, we have a list. And if we have a key and a value, that's going to be separated by a comma in a list, not the dictionary where it does a semicolon. And then we have a tuple then, is exactly what we're going to have. So if we did this, just so you can see it, let's print y. So you can see now that we have y is now, it started out as an empty list, and now it took exactly what we're going to have down here. So based on this, you can see that we have two unique elements. We have I and we have S, which is true. We have two unique elements. Last time we only returned the I because that alphabetically became first. That came first in our sentence rather than our string. But now this time we should be getting an I and an S because they both have a key value of 1, the lowest values. So what it did was it sorted, it took our character count, our dictionary, it's a character count by the items, and then it sorted that. And it sorted it, well, how? We had to tell it. We wanted to do it by lambda. We want to sort it by not the first part, but the second part, which is this is 0 and this is 1. That's where this is coming into place. So we want to take our entire list, x, take our entire list, and we want to take that second index position as our key of how we're going to do the sorting. And then I just wanted to print this to show you exactly what that I is going to look like. And of course, this none here is just referring to the fact that we didn't print out our function because we did not finish it yet. So we don't need this in the end, so I'll take it out for now. I just wanted to show you that. So now what am I going to do? So we have y, we have our tuples inside of a list. So we're just going to do 4 items in y, right? We want to iterate through this now. What do we want to do? We want to compare the index position of each tuple. So how do I do that? Well, I'm just going to say if the item, and I care about that position, the second position, if it equals that sequence, forgetting that colon, then what I want to do, we named it all unique. We're going to append it. With what? The item. And then, of course, we always have to give our good old we want to return all uniques. I got to put an S. I didn't put the S there. I apologize. All right, so now they're all the same. See how when you highlight, I get all three, it shows me where all those variables show up, so I know they match. All right, sweet. Let's bring this down to spit so we see everything. So what I did was we created another for loop, iterating through it, and we're saying for each item in Y, and again, this is how we separated them out. If item in that's the second position equals the same Y of the one position for the value aspect of that tuple, then we want to append it into all uniques. So let us debug. Actually, no, I'm sorry. Let's run first, because we do actually have a print statement below, and it gave me I and S. And just for argument's sake, I do want to show you if we take this out, and if I make this a lowercase a, and then we should get more because there's no other A's in there, right? Yeah. So yeah, see, that's what I wanted to show you. So now we have, I got rid of the lowercase, so now we have one unique upper I, one unique lower a, one unique upper a, one unique upper p, one unique lower s. Now it's kind of being a smart ass because we both know that those are not unique elements, hence the lower method that we're applying here, so that we only get the real ones that are resulted only one time. So let us debug. Get out of here. So I'm going to run my debug on the non-repeats. Excuse me. And I'm going to F8. So it's going to put I apple 8 peels into our string for the argument in the function. And all we're doing here is replacing all of these spaces with no space and lowercasing the entire string. Character counts empty dictionary. Nothing new there. We already saw this loop before. It's going to be the same exact function. So let's go through this. Come on, baby. S. Awesome. So now all uniques is an empty list. So we have that in memory. And then Y equals the sorted to the character count by the items. And how are we doing that? We're using a lambda, which is the function of the self. And we're telling exactly, whoop, let me get this other way so you can see that. What we're left with exactly what we printed for Y before. That same kind of a class list. It's with tuples. So you can still think of it like a key value, but it's not. It's more of a index position 0, index position 1 within each individual tuple that comprises the list. So for item in Y, well, it's going to tell me what is item in Y. Well, the first item is I1. So for item 1, well, item is right here. This is 0. This is 1. If it equals Y of the first index position, the second index position, then all uniques dot append item. So now you can see that was true and true. So in all uniques are empty list, we appended it with the I1 because it equaled 1. Now we're going to go F8. Second item is now S1, so it should also add that. S1. So it's going to go to the next. Oh, why'd you freeze on me? So now we have A, and now A happens twice within the string, so it does not equal that one position. So it's not going to go to the line 23 of the all uniques, so we're not appending our all uniques list. Same thing. We have a 2, we have a 4, we have a 4. Did not work in the sense that we did no longer hit a 1 in that second index position. So we're returning all uniques, non-repetitive. So in our console, we should be left with F8 through that last list. The only two elements that were non-repeats throughout the entire string, and the count, which we know is going to be 1 in this case. So I feel that this one is much more productive, that this particular code, simply because of the fact that we were able to return all uniques, all non-repetitives within that string. And that non-repetitive is obviously going to be based on the lowest key value. And again, this has huge implications in data security and encryption. So with that said, guys, have an excellent day, and I will see you all at the next video.